start, a few things. First, this is the schedule of the microconference. We're going to be starting in about another 5 minutes once Vineet finishes uploading the latest slides. Second, this microconference is not going to work unless you guys participate. And so, please feel free to join in discussions, ask questions. I thought yesterday's real-time microconference worked pretty well. And we'd like to continue that today as well. Some things to keep in mind. Be respectful. So, let's try to keep it nice, clean. Keep your microphone and camera off. We're going to also use this as the catch box that we used at the conference last year. So if you have a question, turn on your camera. Someone will be keeping an eye, or turn on your microphone, and we will get you into the discussion at that point in time. Another thing to keep in mind is let's try sticking to the schedule. This is being streamed live, and so people might want to join into this microconference and see what's going on. And if you're not sticking to the schedule, then they won't be able to see what's going on. Finally, this year we have shared notes. Help us out keeping track of discussions, taking notes in these shared notes. And Vineet, how's it looking for you right now?
Can you hear me?
Yes.
Okay, let me share my camera. Okay, thanks, Dhaval. While I was trying to upload my presentation, like the presenter changed from me to you. So let me try it once again. Oh, it went again.
Why don't you send me the slides by email and I'll upload them for you.
Okay, good. Doing it right now. Just a second. Yeah, sent.
Yeah.
Dhaval, did you get it?
Yes, and you should have it now.
Great. Thanks. So we have 1 more minute to go.
I'll just quickly add that if everyone looks to the bottom left of the course scheduling slides there, you'll see a little download icon. You could be able to download your slides or download the slides right now if you like them.
I think we'll start now. Thanks. Thanks everyone for attending. My name is Vineet. I work for Microsoft, and me along with Julian and Joel would like to drive the discussion about course scheduling. And the main agenda that we have right now is the first thing is like how do we get this feature to upstream. We would like to discuss the plans that we think is a way to actually get the feature to be upstreamed. Then the second main topic I would like to discuss is the interface and discussion, the API that we need for course scheduling. As of now, we have a C groups API, but it has some drawbacks, and different use cases need slightly different mechanism of how to get things done. So we would like to finalize on what or get a consensus on what the interface should look like. And if time permits, we would like to discuss a couple of technical aspects of this feature. One thing is about how do we compare priority of tasks across CPUs, and the second thing is how do we make load balancer course schedule aware. But if we cannot get to it, we would probably schedule it as a BOF session. But the two major things I would like to discuss is the upstreaming plans and the APIs. So we had a OSPM conference about a couple of months back, and there was a very engaging and healthy discussions there. At that time, the things that came up was the code needs to be cleaned up, and the second thing was the course schedule did not give complete protection. Like it makes sure that two trusted processes can run together, but if one of the trusted process goes into kernel, then you have a problem, because a process is running alongside a kernel, and kernel cannot trust anybody. So there was a gap there. And the third thing was about documentation. We didn't have a good documentation. We didn't have any documentation at that time. But when V6 was posted, we included the documentation, which is really comprehensive and mentions everything, like what works, what doesn't work, what are the gaps currently, and how things work as of now. And the kernel protection patch that came with V6 had drawbacks, and we got real good comments from Thomas. So a new version of that patch is posted now. The V6 patch that we had only tried to protect kernel when an interrupt happened, but syscall was a major gap. So if one of the process goes into kernel through syscall, then there was no protection at that time. But now the latest patch that we posted after V6 have the generic kernel protection. So if the kernel is entered from a user land, then you try to make sure that the other process gets paused until the kernel comes out of it. And we had hot plug crashes in the first few versions of the patch, and that's also fixed in V6. But interface and API is still not finalized. We are still using C groups. In the upstream mailing list, what we use is the C groups CPU controller, V1 controller, and there is a tag file over there by which you can tag the processes. But different people using this patch, they have maybe a homegrown patch to actually implement the interface. So this is the plans that we have. Can we take a phased approach? So we know there are a couple of gaps right now, but the feature works. So we can have a different phases. For the first phase, we have V6 plus a couple of patches. Then probably a strong round of review can happen and identify the critical areas that needs attention. And we will fix all the issues. Like if after a review happens, we will try to fix all the issues that are deemed important or blockers. Then come up with a V7, and which V7 will be like guarded by built-in options and runtime options. So it will not be enabled by default. And disabling, like having it disabled in the kernel, we need to make sure that there is no performance impact. It should be like vanilla kernel. And then once the phase 1 is completed, we can move to phase 2, where we work on fixes that are not deemed important or critical. And and then make it complete. That's the idea that we propose. So I would like to take it to discussion from now and see what people think about it.
So if you go back to the previous slide, Vineet, and I guess this is a question for Thomas more than anything else. Why does the scheduler care when we've gone into kernel from user? Why should core scheduling care about it? The scheduler doesn't really care that a syscall has been made. Shouldn't that be part of another mechanism?
I don't know. Why do you think the scheduler shouldn't care?
Oh wait,
Because
Thomas, can you lower your volume on your microphone because you have it's a little distorted.
I mean, because going into kernel mode or user mode shouldn't have any impact on the scheduling decision at all.
So, probably Thavel,
I don't know.
yeah, it's much better. Probably I can take a higher level shot at it, Thavel. Like the main idea is core scheduling makes sure that two trusted processes are running together. But suppose, say, one of the process goes into kernel by a syscall. At that time, it's not two processes that are running together. It's kernel and a process that is running together. Kernel can have a lot of secrets within it. And if the other process is not, like, kernel cannot trust anybody, right? So you need to make sure that when the kernel is running, it should not leak any secrets to any other untrusted process.
Right, but I thought we kind of agreed that was a third mechanism or some other mechanism, say something like, address space isolation or something else that would take care of that, as opposed to the scheduler becoming even more complicated.
No, I mean, the thing is that if you have the scheduler decides what is running where and when. And if the scheduler says, I have an untrusted process running with two threads on two hyperthreads of a single physical core, and I allow it to run in user space as long as it wants in parallel, because they can snoop their own data. They can access their own data, so it's totally irrelevant. But at the moment one of those goes into the kernel, depending on other protections of the kernel, the scheduler, if they are not there, then the scheduler wants to be informed and take the other one out. Otherwise, your whole concept is completely screwed.
But Phil, so that means
the same thing like interrupts.
Well,
so hold on. So then that means
different from an interrupt.
So then that means we also need to be tracking every hypercore. Are we doing that?
Yes.
We are.
Would it be possible to do the kernel user protection thing by, instead of adding code to the scheduler, having some architecture-specific code that piggybacks in the IRQ time accounting code? Simply account the time as IRQ time, so it will later on be subtracted from the user time. That way you would not have to modify the scheduler itself.
What solves the accounting? How does the accounting do any protection? I mean,
IRQ time gets at the end of a time slice when time is accounted or at a timer tick. The time spent in IRQ time is subtracted from the amount that is accounted to the process.
No, but we don't want them running at the same time on the.
It's not.
Wait a moment. I'm missing something. So you talk about accounting, but on the other hand, you talk about the scheduler making sure that only two threads of one process can run on the siblings. So what the hell is accounting about? I mean, if one of the siblings goes into the kernel, then your assumption that both can happily share the physical core in user space is gone.
Oh, agreed. The other user space task needs to be preempted by some architecture code that makes that sibling thread idle.
Yeah,
for the
that's
duration.
that's what we do
Not
currently.
the problem of why architecture code, folks? It's
Because it's an x86 only issue.
Are you sure it is? As far as I
No.
understand, Thunder X2 has SMT just the same, so I don't think it's architecture specific.
no, pretty
Okay.
much every SMT architecture has the same problem.
Yeah, the way we have designed the current patch series is we have tried to avoid being architecture dependent as much as possible.
So basically, what the entry code should do on the syscall, if the internal kernel state is, hey, you're one of the, you don't or not allowed to enter the kernel while you're attacking or potentially attacking partners in user space, then this has to call somewhere in the core code, and the core code has to react on that. It's not, don't go and make that in any way architecture dependent. It's completely wrong.
That's how we do it right now, Thomas. Yeah.
So and we have exactly, that's one of the things why we started to have the generic entry common code. So you have one single place where you want to do that. And every architecture which wants to utilize that stuff should convert itself to the common code.
So
Yeah,
Thomas,
crap.
Sorry. I was just going to ask Thomas, does the last patch series look okay to you, or did you look at, you had some comments on the earlier ones related to stop machine
I
stuff.
haven't looked yet at in detail, so it's on my ever-growing backlog.
Okay.
So just to clarify the different state changes, what are the state changes we're looking at?
So,
We're looking at
Thavel, just to clarify, as of to Thavel and Rick, like scheduler is not really involved in this part of the patch. So what happens is, as Thomas mentioned, as soon as you enter the kernel, the entry level generic code pauses the other thread. So scheduler is not really involved in this, and I think.
right.
So,
but what are the state changes? What are the state changes we care about? Do we go from guest to hypervisor? Is that a state change that we
Yes.
are?
So currently we care about kernel entering kernel mode from user mode or from the guest mode, and the patch also takes care of idle to kernel transition as well.
So I just wanted to clarify that the scheduler is sort of involved, because we do look at the run queue data structures, and we try to figure out what is running on a run queue and stuff like that. We acquire the run queue lock, and so in a way it is involved. But yeah, like to Vinny's point, it's not making a scheduling decision, but rather the code is in the scheduler core.c where.
It's not making a scheduler decision, but the scheduler is the place who knows about whether the other party needs to be taken out of user space or not.
Right.
My question is, I have a question real quick, just about entry. Once you enter into the kernel and then you get to the point where you're saying, okay, you have to get another sibling off the kernel now, is there protection? Is there a way, I'm like, is there a flaw in the design here that the sibling, if you have an untrusted code, can find a way that I can, somehow speculate the entry for that logic that does the switch to find some secrets as well? Is there any concern for that aspect? And I hear Thomas's dog has a comment to that.
Yeah. No, I don't think so. I mean, we never will have perfect protection against anything, but at that level of entry, and this happens really, really early, there's not much to speculate.
Okay. But I guess, wait, I'm just curious, I haven't looked at the patches in a while. So what's exactly, when you find this happens, what do you do if the thread that's happening, you just you kick it into idle? You force it into idle, or is that?
We send a IPI to it. We currently use IRQ work to implement that, and we basically force it to enter the kernel through that, and then once it has entered the kernel, we don't need to do anything in the IPI handler. When that IPI returns to user mode, like we have the regular return to user mode checks that wait to see if it's safe to return to user mode. So all we have to do is force it into the kernel, and then it all just works.
Does it give it a new running state saying, hey, I'm dangerous to run by myself?
So that state is marked like by the user already, like it's all the tasks that are tagged.
Right, I'm just saying that so you got to check to see before you start running it again. You got to make sure that I guess where the scheduler is involved, where the scheduler has to say, okay, everyone on this core is safe to run together. And
we track that across all the hyperthreads. Like we know when each hyperthread on a core is in the kernel or not, and we wait for all the hyperthreads to exit the kernel before we know it's safe to return to user mode. Yeah. So
Conrad, what did you have to say? Okay, audio is not coming through. Do you mind typing your question? Was your concern kernel secrets?
Well, my point was that everything in the kernel has secrets, or kernel has access to most everything, except for some new memory layouts that are coming too. But I figured that if you have access, the whole point is to keeping the kernel from running as well.
So I was going to say, other than the IRQ protection, do we want to bring up anything else we need, like things that are blocking upstreaming? Or is that the next slide?
Yeah. So
sorry. So V7 is not feature complete till we have interface sorted out as well, right?
Yeah.
Your fourth bullet.
Yeah. So there are two approaches that we can take. That's why I put the bullet here like this. One is like we need to come up with a consensus and then develop the API completely, and then have V7 and then go about merging it. And the second option is like have a minimal API like what we have right now, because the different people who are using this feature as of now, they have their own homegrown versions. So if it doesn't seem to be a blocker because everybody has their own thing to use right now, maybe we can have the minimal API as it is and then work on a full-grown API in the phase 2. Like I just want to put forward these two ideas.
Yeah. So then the question is, I guess, what does a minimal API look like, right?
Well, so I'm not convinced that it's a good idea to have a minimal API and have every user out there have their own out-of-tree API, because then we're just going to spend all of our time fighting about whose API is better and why we should fix to that, because we're going to have tons of users on those out-of-tree APIs. I would much rather that we spend the time in advance now figure out an API that works.
Okay. Yeah, seems fair. So the only reason I was putting this was it's not that users are going to implement their homegrown APIs. They already have something, so they will not be blocked right now. That was the idea. But I agree to your point that we need to spend, like, it's better to spend some time coming up with the APIs and then implement it.
Yeah, so that sounds good, Vineet and Dhaval. I was actually thinking from another angle. So right now, with hyperthreading off, that's like, security fix, right? People turn off hyperthreading. So one way to do this would be to if we can come up with an interface, we need to start somewhere. So one way could be that, on boot, we make everything untrusted. Everything is tagged by default. And so the system will behave like SMT off, but at least we will have something upstream, and and then we can incrementally work on the interface. It's just an idea, but that would be one approach as well. How does that sound to you guys?
So how would one use the feature?
So yeah, I mean that it's incrementally being improved, right? So the point is that by default, the code that we are developing here and all these issues that we're working on, vRuntime, hot plug, and all this stuff, at least we will be able to incrementally improve these in the upstream code without worrying about interface forever.
But Joel, how do we know that the code works if there's no interface to mess around with things?
So it depends on what you say by work, right? Like, I know as a user of the feature, you want to have an interface and see it working, but I'm talking about the infrastructure and getting that into good shape.
What's the point of great infrastructure if you can't actually core schedule when you do things?
I'm not saying that will be the case forever. I think you're misunderstanding. It's not going to be like that forever.
Joel, what you are proposing is to put something in place in the core part, but without any use from the main line.
Yeah, exactly.
But usually we don't add a feature which can be used. I mean, if it can be used, it can be tested, and if it can be tested, there is no way.
So yeah, that's the thing, right? We have found bugs in this code by just by not even having an interface. Like, we've found performance issues and stability issues and stuff like that. So a lot of work has been done even without having an interface here.
I'm just curious if you tried to, I don't know, I'm just throwing this out since you're talking about phased approaches. I'm saying, say if you had, so all processes would run on it, like if you set up, have hyperthreading on, but almost run as if it was off, where everything runs on one thread of the CPU. Unless you had, for example, if you were scheduling kernel threads, all kernel threads could go anywhere except if it's running. It will avoid running if a process is running. So, and maybe do it that way. So if you could have the scheduler say, hey, the CPU is only kernel threads. You could add another kernel thread. If a process comes on it, boot the kernel thread off, or hold off that process from running until the kernel thread's done and goes idle again. So basically, processes, if you had something where you set up so processes only run if the other threads are idle, then you just run it that way and see what maybe you get a better performance gain, and then you maybe can do performance checks before you go into further, because I think that's probably would be the easiest step to do. I don't know. I haven't been working on the code, so.
But do you feel like that would be okay for upstreaming?
If it showed an improvement.
So from a performance standpoint, it's definitely not going to be better than SMT off, right? Or are you saying that kernel threads can run together? So
right, kernel threads could run together. So at least for kernel threads processing. So say if you're doing networking, say if you have a lot of network I/O and a networking processor just processing a bunch of packets and sending it off, where maybe so if you had one core doing a bunch of networking codes, and the processes that are taking those codes are on other cores. So user processes, I guess, are still, they take up a full core. The thread will just always have to be idle, and then you might for those type of services where you're doing high network traffic, where there's a lot of driver activity, maybe that would be better. I don't know, But then again, a lot of those networking things will usually be a user space process that mmap, or that basically mmaps the networking card and does all the processing in user space. So then you lose all that anyway.
Yeah, in this case, don't we will lose all the main goal of this feature to protect again any attack. In this case.
But how would you get attack? You couldn't be able to do any attacks, like you said, as long as processes are only run against idle. So idle shouldn't be a problem.
Yeah, I think Vincent thought you said that you would have users share, user space share core, which we don't want to have. But yeah, I think he got what you were saying, Steve.
Yeah.
And anything, like I said, if you had a proof of concept, at least that gives you an idea of, working out the bugs. If you want to try to see if you get processes that could run together and then force one into idle.
Yeah.
Either
so
that
sounds like a good idea. Actually, it might be worth looking into. One of the things is what we seem to be having issues with, discussed on the list as well, is the vRun time comparison. And essentially, like, what we want is when you have a single run queue and tasks competing for that run queue, that should behave approximately the same as if you had two tasks running on two different hyperthreads, and we're trying to figure out which one gets to run on its own hyperthread. So we essentially, when two tasks don't trust each other, we treat the two run queues as one run queue. And we do comparisons between the vRun time across the hyperthreads. And there are issues related to the minimum min vRun time value. The min vRun time can be different for the two run queues, and so there are issues where it looks like there is unfairness. It's not like as if you were running on a single run queue, and so such issues can be sorted out even without an interface if we had some way of having this infrastructure upstream, and we had a way for everything to run with SMT off, and we could sort these issues out upstream. It's just a thought. Like this does not require an interface, right?
Well, is Peter Zylstra on? He's the one you might want to ask about.
No, he's not.
No.
Yeah.
There are a couple of Peters on, but not.
Thomas, say something?
I just talked to him and he said, no, he's not interested in having the same discussion which was had in Pisa again. And you should get your act together and just agree on something useful. I mean, you need an API, otherwise it's just pretty pointless. I mean, you need at least a concept for an API. There's nothing wrong to merge preparatory stuff, which is required for the full solution piecewise. I mean, other big projects do the same thing. You have it. So the important part is that everyone agrees on that we want to have it at all, and once you have that agreement, then you can go and say, okay, here is the config switch which disables that crap. You can't enable it right now, so look at how we do it for RT. It's the same mechanism, and then you add the bits and pieces infrastructure wise, and then once you have an API, you can actually enable it.
Yeah.
Why are we conflicted on the API? I'm like, has there actually been any pushback on just using the C groups and cookies parts?
So the issue seems to be C group v2's flexibility, and people are concerned that. So I guess this is a good way for us to discuss the interface itself and what we've been discussing upstream. So do you want to pull that up, Vineet, on the screen, the mail thread?
Yeah, so probably, Joel, you can go discussing this generic thing, and then I'll pull the mail thread at the meantime.
Okay. So I work at Google. So for our use case, we have people in Google Cloud using course scheduling, and we have on the Chrome OS side as well. We have folks using course scheduling. So for the Google Cloud use case, what we have is we have these containers that are created for different jobs, and each of these containers is tagged. It's like a C group, and then within those C groups, we have sub C groups, and those sub C groups have their own have this thing called a color, and the idea is to split the assignment of the tag into two parts. Like, so you have a privileged user who can set like the first level of the tag, so that the containers are isolated from each other, and then within each container, the process, an unprivileged process can set a second level tag for each of the sub C groups. What this allows us to do is the root daemon that creates these containers at the root level has already isolated the container, so it doesn't need to worry about what happens within the containers. And then within the container, an unprivileged process can do further isolation. It can, set the second level tag to the same value for some sub C groups, so that they share a core, versus while not having to share a core with other sub C groups within that container. So that's the use case. I think, Vinny, it might be better if we pull up the email, and there's just too many details to talk about without slides. Yeah. So the second use case is the Chrome browser. Each time a tab is opened, what we do is we tag the process that is that tab. It's called a renderer. It's already a sandbox process, but we also call a PRCTL. It's a homegrown PRCTL interface that we call to tag the renderer, and we also tag all threads that are forked within that renderer. So essentially, SMT is turned off for the renderer. So can we go further down? So for Chrome OS VMs, we tag each vCPU thread as well from the VMM side. A concern is that the VMs can run arbitrary code and attack both the guest and the host that are sharing a core. So we tag all the vCPU threads in the VMM itself. So these are all pretty simple use cases, but of course we have to agree on an interface and what it looks like upstream. So that brings us to use case 4, which is there are concerns by Chris and Dowell that when you tag like a C group hierarchy, everything in that C group will share a core, but maybe some sub C groups don't want to share a core with everyone in that C group. Primarily, this comes down to C group V2's unified hierarchy, and the unified hierarchy is like already decided, and so it's a little inflexible with regard to having more finer grained sharing of sub C groups and stuff like that. So that's a consideration that Chris and Dowell brought up. Can we go further down the list? Can you scroll? Yeah. So So to solve all these use cases, I sent out an email 3 or 4 days ago. So I was for use case 1, which is a 2-level tagging mechanism. I proposed I was suggesting a Boolean tag file in the CPU controller C group, and if this tag is set, then that C group and all sub C groups will be tagged. And if it is reset, then it will inherit its parent's tag. And I also suggested a second file in the CPU controller to manage the color. So I was thinking that this would solve the first use case.
Yeah. So
yeah, go ahead.
You can hear me, right?
Yes.
Okay. So I actually think this looks good. I know Davo had some questions, right? But so let me just say, right? So in the multi-tenant hosting environment, clearly we have to support C groups, right? They already exist. They're already set up either for VMs or for containers. But I don't know that we have to go, maximally crazy to support every possible thing. So as long as the normal reasonable case works, and then as long as we can override on a per task basis, which I know is part of this, I think that'll work. So I actually like this, because this does in fact allow delegation of C groups and containers, and somebody's going to want that, right? So
when you say overriding, what did you mean? Could you clarify?
Okay, so if I have a task that's in a C group, and because it's in that C group, it gets a particular tag or cookie, right? We'll call it cookie. I should be able, via the per task interface, to go set some other cookie. That's what I mean by override. So a per task cookie would override a C group defined cookie, right? And I think that was your plan all along, right?
Yeah, but that makes no sense.
Okay, how does that make no sense?
Well, because then I look at tasks, and my expectation is, okay, these are all part of the C group. They're part of the same core scheduling group. But in reality, they're not. And how do I figure that out?
Yeah, so to figure that out, I was suggesting in this email that we would have a file inside the C group itself that would indicate which of the tasks do not, share, are not subject to the C groups.
Have an exceptions file.
Yeah, something like that.
Exceptions. So now you give me a list of exceptions. Now, when I look at these exceptions, how do I know which one of these files are entirely untrusted or form their own trusted group? Do I now run the per task interface on each one of these threads?
The C group file will tell you which ones have been overridden by the per task interface.
Yes, but then do they tell me that if, let's say, I have 5 of these exceptions, are 3 of these form their own trusted group and 2 of them are untrusted? Or is it something else? I mean, the reality is that this interface has too many questions.
Yeah, I mean, I'm all for years for ideas. that was the point of bringing this up, right?
Right. That's why we're talking about this. But I have looked at C groups from the user space side for a number of years, and I've had users come and ask me questions. I was very happy to give up that project when I did, and now it's come back up again. And this interface doesn't work for that reason.
Okay, so let me see if I understand. So you're saying the inability to read anything within the C group directory to figure out what is or is not trusted, that's the problem you're objecting to?
Yes.
Okay.
So if you look at CPU sets, for example, as Joel quite rightly pointed out, CPU set takes priority or precedence over the task set, right? You'll have to move the process outside of the CPU set before you can change its CPU affinity mask via it is using task set, which the equivalent is the per task interface.
Yeah, so I was also saying by email that that's hard to picture with core scheduling. Like it gets confusing if you allow that to. Like we totally want the per task interface to override the C group one, right? Don't we?
I really think that that's against the delegation model in general, the idea. So the task has to be restricted by the C groups. So if you want to implement something like that, maybe a way can be that you assign a set of colors to a group, and then the task can restrict and pick one of the colors allowed by the group level. And then maybe in that case, you can say, okay, the tasks under that group can choose between color 1, 2, and 3, and you pick one. But it has to be a restriction. And the CPU mask example that Dhaval called out is actually makes sense. So you define the maximum span at the group level, and then the task can restrict it. Otherwise, the delegation model is broken.
Actually, that might work.
So there was a concern by Dhaval and Chris, you guys, on C group V2's unified hierarchy and how someone might be stuck with a hierarchy, and that might work against something like this.
So I mean, I just want to point out one thing, right? The whole C groups V2 stuff, that boat sailed. So there's no point in having the whole C groups V1 versus C groups V2 discussion. I also don't see any point in coming up with a brand new pseudo FS C group. Call it course get FS.
Okay, right. But the issue with the V2C groups is the hierarchy could literally be defined based on the needs of completely different controllers. And how that maps to your trust model, it may not map to your trust model in any way, shape, or form. So the theory is, well, you could always carve off a child C group, I guess, somewhere, and by shifting the right stuff, maybe make it all work. Or you allow a per task override. So I get the notion that a per task override somehow defeats the whole C group thing. And that's actually kind of the point here. That's just my thoughts.
It mostly defeats the trust model, right? That's the big problem.
Yeah.
So why can we not just make all that delegation and decision part of the container overload process or whatever you have above you, that can then just create a second C group for your task if you have the permission to also run in a trusted mode?
Yeah, that's exactly what we were talking about when Patrick suggested to, at a high level, have multiple colors available to the parent, and then you delegate it, have multiple.
I don't think it has to be as complicated as multiple colors. Like if you literally just say a C group is like explicitly set to, like it all, core scheduling is only enableable. Like you create a C group, you only have the ability to enable C group, enable core scheduling for that C group and any children underneath. If you really have a child that does not want to have core scheduling enabled, you just delegate that the creation of a new C group that doesn't have that task, that bit set, to something that created your C group in the first place. It doesn't. We don't need to push it all down to the exact same C group semantics and all of the same groups down there. Like,
but the problem is, having created that C group, it now becomes part of the hierarchy managed and controlled by all of the controllers that are enabled in V2. Now I can maybe disable various controllers on that particular C group, but what if that task actually had to participate with controllers in some other manner? Now all of a sudden I have security needs that make me want to put it in an isolated thing by itself, and I have actual resource management needs that make me want to manage it with the resources for which it actually shares, accesses, etc. In fact, the only reason it's distinct here is its security requirements. And it's important to note that we only get our performance back if we bother to trust trusted processes, right? So if it's trusted, we need a way to market trusted. I mean, that's all this was about.
I see conflict messages, 5 minutes and time is up at the same time. Which one is it?
Well, according to the schedule, it's supposed to be at 10 of was the...
Okay, so that's the right one.
We postponed it for 5 minutes at the beginning.
What? Oh, because you started 5 minutes later, you moved it? I'm just looking at the schedule, but I thought you had that included. Okay. Well, your actual schedule says 7 to 7:50, but because if you started 5 minutes later, continue for 5 minutes then. We'll reset the timer.
But then we get a 5-minute break.
So could you scroll a little bit beneath? I just want to talk quickly about the other interfaces other than C group that we are thinking about. So yeah, so Peter had suggested, and it seems like a good idea, which is to define a PR cuddle or some system call where you provide the PIDs of the process you want to share. You're okay with, you want to share a core with, or you want two processes to share a core, and then you could do the ptrace may access checks within that and make sure that they're okay with that check passes basically. So that could potentially work hand in hand with the C group interface, whatever that might look like. We still have to figure out how we don't confuse the user of C groups, their expectations based on what this API does. And also we have to figure out how this works with the, how it works with analogous to something like CPU sets and the delegation model that Patrick brought up. So that's all still open. And the next thing is the behavior on fork. And there seem to be different needs, like different users want for scheduling, want tagging to behave differently when a fork happens. So, that is so I was suggesting a couple of clone flags that would essentially determine what happens on a fork, whether what is being forked is trusted by the parent or not, and stuff like that. So some other considerations. There's an open question. This was suggested by Peter about, that we don't always have to enforce core scheduling if the CPUs are not vulnerable. But this assumes that core scheduling is all about security and not about other use cases. I don't know about other use cases. Our use case is security. But if anybody had any thoughts on that, we could discuss that now.
Yeah, we have a couple of other use cases where I remember there were some use cases in RT and users wanting to have processes given a core on their own, which uses SIMD instructions and those kind of stuff. So, but the majority is basically security.
Right. So basically, there's no point in giving away performance for the security case, at least, if you don't need to, right? So.
Sure. If you don't mind, do you think we should have a BOF for this? Because I think this is actually an interesting discussion, and we are almost out of time.
Yeah, I agree. Yeah, let's move it to BOF. Yeah, hopefully sure. Peter can join. Enough people pressure Peter to join. Okay, this was very useful though. So thanks everyone.
Thanks everyone. Yeah. And yeah, probably if you could have a couple of BOF sessions. So if you can have a couple of BOF sessions for VRuntime and other things, then that would be great.
Yeah. Thank you.
Are we ready to start?
Hi. Yes, Vincent. You should have presenter now. So it's 8, and our next talk is by Vincent, talking about the load balancer and how the scheduler is going to move forward. Vincent?
Yeah. So yeah, that's I'm going to speak about the fairness of the CFS scheduler. So let me there.
Vincent, before you get started, request to everybody helping out. Could you please help us taking notes in the shared notes section?
Okay. So yeah, that's the problem that I'm working on for a while now. It's how to balance the running time between tasks when your system can be balanced. So typically, if you have 9 tasks on 8 with 8 CPU, how do you make sure that all the tasks will get the same running time? So that's I already discussed about that at OSPM in May. In the meantime, I have done for the test and development, I have new result and also new problem. In fact, problem once I'm fixing one problem, another one is raising. So I'd like to share all the results during this session. I think we have something like 30 minutes. So I will go quickly on describing the problem and the main issue and also the current solution that I have for those for which I have a solution. So yeah, so the fairness that I'm speaking about only apply in for some use case, and especially when you are overloaded, because if your system is not overloaded, we assume that there is enough runtime on the system. It's just a matter of migrating the task on the correct CPU to let him run. But that's the main problem that I'm trying to work on. So those results, so for testing the fairness of the scheduler, I'm using RTApp, where you can run some simple use case. So typically 9 tasks, which are always running, and you can count the number of loop you're doing for each task. So in this case, it's an ARM64 platform. So the average unfairness, so the unfairness, it's the ratio between the max running time for one CPU and the min one. So the ratio can reach up to 20%. And so I was running several iterations, and for some iteration, the difference was more than 40%. And if I remember correctly, I have been able to have a use case where we were almost to the limit of 50%. So this is a kernel shark snapshot that try to show the problem. So we have this 9 tasks on the 8 CPU. And it's only in this sequence, which is 5 seconds long, it's almost always the same task that is migrating over, which means that this task always have only half of the running time compared to this green one, which have a full core for itself. So we have almost 50% of running time difference between these two tasks without any good reason. And so right now, and one of the problems is that right now the 2 rules to migrate the task from one core to another one, it's the load of the task, and this one should not be more than twice the imbalance, which is not often the case in such situation. Or also the other case is that when we have failed too much time to migrate the task, then we just take one and we don't care anymore about which task is it. And so we end up typically pulling the same task across the use case. So yeah, so this is the first 2 problems that I have faced. So one problem, it's the simultaneous busy load balance. So most of the time, it's not always the case, but most of the time, all the domain are triggered for load balances at the same time. And it's mainly because the interval right now is based on the weight of each domain. And we are using on top of that a factor, busy factor, which means that everything has got the same mean granularity and all the load balance are happening at the same time. And because the larger domain have more CPU on which they have to collect statistics, they usually try to pull a task a bit later than the other one. And when they try to pull a task, this task has already migrated on another RQ in the domain. So the solution that I have found is working quite well. It's just to decrement by 1 GFIS, the busy interval. That's helped to make sure that all the load balance will not happen simultaneously. It's quite easy to do, but it's, I would say it's 90% efficient. Another problem, and for that, I'm interested to get some feedback. It's the busy interval. So when the CPU are running, we are applying a busy factor, which is 32. On small system, like 8 core that I'm using for my test, the value between two load balance stay, I would say, reasonable, with a bit around 100 milliseconds or around 250 milliseconds. Different depending of the level, but on large system like this 2-node system with more than 200 cores, the load balance when system is busy can reach 7 seconds, which means that the load balance between the 2 nodes will happen only once every 7 seconds, which is quite huge. And my goal would be to decrease this. I don't know if some people have use case where they need to have this very large load balance period, but this seems to be really, really high compared to the system that we have right now. And even at the MC, in my case, even at the MC level, so where the core sharing their cache, the load balance only happen once every more than 3 seconds. Whereas we have some cache sharing benefit. So right now I have only decreased the busy factor from 32. I decreased that to 16, and I have seen some improvement. Yeah, I have seen that there is a comment from Alexander. The main problem with the HR tick is that this decrease your performance, because you will, for example, you will have a lot of timer event that will happen and first scheduling switch. So the throughput of your system will decrease. I don't know exactly by how much, but it's significant.
I can at least think of one use case where we would like to avoid migrations as much as possible. So even 7 seconds might be too low.
Okay, yeah, but in this case, that's another problem. You want to disable load balance, which is possible. I mean, that's possible with the C group. But in this case, yeah, that's my point. I mean, does it really make sense having this more than 3 seconds or more than 7 seconds between two load balance? In this case, it's probably better to disable the load balance and do some static or user space-based load balance or CPU affinity, something like that. So yeah, I'm open if you have any comment on this, on the right values. So yeah, I have done several tries. I have tried, instead of using right now we're using the weight, the number of core in the skid domain to define the interval. I've tried to use a kind of log like for the skid latency. Maybe it's a bit too aggressive because the value the period can become too short in this case. So yeah, I will continue to work on that, but I'm open to any advice.
So I have a really stupid question.
Yeah.
What's the performance throughput cost if you're balancing more often?
I don't have number to share, to be honest. Yeah, maybe I should run, but for me, yeah, that you will. I mean, you can.
So the reason fairness is really nice here is it would improve interactivity.
Yeah.
Right.
Yeah.
And systems this big, I don't think try to really be interactive.
So yeah, and another use case about this fairness problem will be if you're using some parallelism algorithm. So you start 200 or the number, depending of the number of cores you're starting as many threads as you have cores. But if you have some background activity that delayed only one, you will lose some performance.
But then that's an HPC use case where they anyway don't want the scheduler in the way.
Yeah, maybe. There is a comment from Mel as well. Consider a large database with many transaction threads that overload. You want each query to get fair progress.
Well, but yes, they want, but more often than not, we don't really care about tail latencies in that case. We really care about getting as many things done as quickly as we can. And
yeah,
if some queries take longer, that's okay.
Yeah, the main problem is that you can have some part of some job which gets stuck for a long time, which can become critical. I agree that the interactivity is not only the problem. But for example, in the case that I was mentioning before, if I'm coming back there, so whatever is the green task there, it will take twice more time to run, which is significant. And here it's only about computing things. So yeah, so that's the two. Maybe I can move because this one I would say are not some major problems. So another problem is the task selection. So I have tried 4 different solutions. The first one, I was monitoring the average increase of the mean variant time to see if if the mean variant time of one run queue was progressing faster than the other one, meaning that the task has more running time. But to be honest, it was not good enough because it was per run queue statistic. It was not taking into account when a task was migrated. Then I have used another solution, which was so the load reflect how much work you have to do on your run queue, whereas the weighted average ratio give you how much running time you have. So if you give the ratio, normally if you have the ratio of load versus utilization should be the same for, I would say, all the tasks or all the run queue between the run queue, which would mean that everything is moving at the same pace. But using this, because of the half period of the pelt is only 32 milliseconds, and comparing to the load balance interval where we are more than 100, 200, or 1 or 2 seconds, we lost all this transient state. Also, Peter, so I discussed with Peter, is not there, but we accumulate some, we discuss about accumulating this imbalance between the run queue on a shared data structure. But for me, it was a bit too complex because you have to accumulate some shared data, then you have to clear that once the other run queue is finally balanced. So it was a bit too complex. And the last one that I have done is that I have played with right now, we have 2 states, which is we try to pull a task with a load, which is no more than twice the imbalance, or we can take any task. Instead of doing that, I'm using the number of, oh yeah, no, it's not cache nice. It's the number, yes, of a failure. And instead of doing that, I'm using the number of failed load balance to decrease the constraint of the task that we want to pull, which means that the first time that we are doing a load balance, I will try to get something that match exactly with the imbalance. If it's failed, then I'm using the right shifting. So then I will try to find a task with a load no more than twice, and then no more than 4 times, and so on. So which means that from time being, I will be sure to pull a task. And if run queue pull the task, you will reset its failed load balance, and we'll go back to asking for exactly the right load. So that's what I'm using right now, and I will provide some numbers later. I don't know if there is anything that could be better than that. The main advantage of this solution is quite simple. It's only one line of code. The other problem is the active migration also, which when you fail too often to pull a task, you schedule an active migration, which can be a bit of nuisance, to be honest. I mean, we have some use case like misfit task, like pin task use case, where doing active migration makes sense. But otherwise, and especially if we are able at some point to pull any task normally, we should not need to do any active migration. At least I haven't found any use case where we would need this. Right now, it was mainly there in case because of this kind of imbalance and the fact that we might be in some situation where we can't pull any task. Sorry, there are some comments on the chat. I don't know. Yeah, that's mainly some comment more than question. Don't hesitate to appear there and raise any question or comment dynamically. That will be easier.
I do have a question actually.
Yeah.
So like over here, are you assuming that all these threads belong to a single application or not? Because in my head, I'm thinking that if there is a single application that's overcommitting the system, I think they better know how much their worker threads are able to do and distribute the work in a better way. But I think we have a problem if you have, for instance, in your use case, like if you have 8 CPUs and you have 2 applications, one is having 3 busy loops and the other one is having 6, how do you distribute fairly then between these 2 applications? I don't know if AutoGroup can help with that or not. But you certainly want to give maybe the application which has 3 tasks more CPU time and let the other application to interleave more. That's what I would think would be like more fair. I'm not sure if this is relevant to what you do.
No, so yeah, all this have came mainly when I was working on the rework of the load balance, and I was seeing this case where some task was running far less than others, which means that this could impact the throughput and so on. So that was my main. That's where I'm started to work on that. Then regarding your use case, it's only about the thread, and that really depends on their weight. So either your 2 tasks are belonging to 2 different C groups, for example, with the same weight, and in this case, we should try to give the same runtime for each group. But I would say that if they are at the root run queue, will not take into account the fact that one process have 2 threads compared to another one having 3. We'll just give the same amount of running time to all the thread.
But this will be unfair, isn't it? I mean, one application will basically run a lot faster than the other.
But we are not taking care of application. Yeah, we are taking care of the priority of the thread. If you really want 2 applications to have a fair share, you must put them in a C group with the same share priority.
Okay, fair enough. I just thought that's more interesting actually of a problem to solve. But yeah, I get you.
And I had a question too. Maybe you're getting to this later. It's also not just about applications over provisioning the system. It could also be something like a big little use case where if you look at the capacity of the CPU and you just have 8 threads running on 8 CPUs, all the little threads are going to take a long time to finish. Is that something you're trying to handle here, or?
No, normally that this should not be a problem with the current load balance, because we have this capacity. Then once normally we will pull with the misfit task, we'll pull the task from the little to the big once the big is has finished to run the other one.
Yeah, but will that happen if they're actively running all 8 threads?
Right. What if they're not misfits?
Yeah. So yeah, no, maybe yeah. Now I get your point, Sarah, and you mean that between the if for example, for the use case I was using, if 4-core or big one and 4-core little one, even if they are running this, they will not have the same amount of capacity. So
Right,
it's not taken into account right now. I'm not.
Maybe
taking
that's
that
something you can want to take into account, and maybe that'll prune away some of the options you have, or maybe it'll simplify some of them.
Yeah, this might be, in this case, I should take into account the capacity. So that's what I was trying to do with the load, the ratio between the load average and the utility average, because you have this capacity awareness in it. But
yeah, I think we definitely need to take capacity into account. Otherwise, it's like going to be broken for a large set of systems.
Yeah.
And also another thing would be capacity doesn't have to be big, little either. I don't know, depending on system, how thermal is going to affect it. If one CPU is in a harder part of the system, we can get throttled more. Do we want to rotate things out of that? That's another thing to think about. That's where utility capacity would also kind of feed into.
Exactly, and the thermal pressure is there also normally to help migrating task.
Yeah.
So these are these are the tests. So for all the solutions that I've provided there, the test results show that now the average and fairness go from, it was around 20 down to 8%, with one iteration, which was 12. But yeah, the maximum unfairness is really low compared to the more than 40-45%. So that doesn't solve completely the always same task problem, but this helped quite a lot. I mean, I can see a significant difference, improvement, with some changes which are not that huge. I mean, maybe we can discuss about the interval configuration, but yeah, I really think that this 7 seconds is way too much for a system, whatever the number of CPU. Or as Deval said, maybe in this case we should just disable the load balance. Nevertheless, so yeah, I have some improvement, but it doesn't solve everything. There are still some issues. So yeah, the fact that the same time is can be pulled, even if it's less the case now. I have another problem with the imbalance threshold. So we have an imbalance threshold. We are not doing some load balance, or we are not pulling tasks if the imbalance is not that huge. But at the die and NUMA level, the imbalance is 25%, which start to be significant. Which means that if I'm doing another test, in this case, so I have 11 tasks, always on my 8 CPU. So which means that I have 5 on one side and 6 on the other one. And in this case, the imbalance is lower than this threshold. And the load balance is not doing any migration at all, which means that we'll have always the same 5 tasks on one cluster and the 6 tasks on the other cluster. And in this case, we have 20% of unfairness. I mean, which is significant, in my opinion. I don't know what's so the point is that should we play? Why are we using this 25% of imbalance?
Historical reasons.
Yeah.
It used to be big, and it's still big. Also, the reason is we want to avoid very frequent migrations, and this is one of the reasons I proposed the incremental addition of imbalance.
Yeah.
And if you do that, you'll at some point overrun whatever threshold you have and force a migration anyway, but at a slower rate.
Yeah. So with what I'm doing, I think that I have something similar to what you're proposing, in the sense that at the beginning, I will make sure to take only a task that will fit exactly, which means that we can reach, if there is a possible static, yeah, okay, thanks, Deval. If there is a static balance that can be found, we'll find it quickly, and then we'll stop to do some load balance. Otherwise, if it's not able, we will wait for several load balance interval before trying to pull some bigger task, which for me is quite similar to what you are proposing. And in this case, I haven't tried, but I was tempted to decrease the threshold because
either let some imbalance increase in time or decrease the threshold, same difference.
Yeah, exactly. Yeah. So that the two main issues that for which I'm working right now, and especially this one to make it. But yeah, I don't see any other solution than decreasing the threshold. But yeah, I wanted to raise that to see if which kind of reason, apart from minimizing the number of load balance, which makes sense. But if we consider, yeah, that was the last slide. If we consider that we are not pulling tasks more often, that might be a good trade-off. Yeah, Mathieu?
Yeah, just wondering, could you tweak the vRuntime? So when you migrate a task, you're actually making it take more cache misses. So you're basically slowing it down. So if you tweaked its vRuntime when you migrate it like this, could you use that to basically make sure it does not get migrated again and again too often?
Yeah, I'm not sure if we can really play with the vRuntime, because when you move on one task, we already play with the mean vRuntime. We already giving him some kind of a gentle fairness compared to the one which already running. I was
yeah, but
mainly
I'm talking
thinking
about changing its rate. So it would basically appear as having less vRuntime, consuming less vRuntime, as it's taking the cache misses caused by its migration.
Yeah. So you want to tweak his weight in this case. That's what you are seeing, in fact, because the weight is what is used. That's probably something that can be done.
Yeah,
but
it'll already be penalized by having to take all the misses. But yeah, I don't know.
Yeah. Also, we already have some kind of cache out stuff that could be improved. But just Mathieu, do you think your comment is a way to improve the fact that we're always taking the same task, or that just something else for the fairness, the fact that when you're migrated, because of the cache, the increase of the cache miss, you don't have less throughput. You have the same runtime, but you are less efficient during this time slot.
Exactly. I mean, the goal there would be to make sure we don't always pick the same task, because if we do, then it's always in cache miss mode, let's say, and we don't want that.
Yeah. Yeah, but we are not using the vRuntime to decide, because that doesn't the vRuntime or the mean vRuntime. Yeah, the vRuntime only give you how much running time depth you have compared to the other one. Now, another thing that we could use for this is the utilization, the opposite. Are we going out of time, Deval? Yeah, 1 minute.
Hey, I kind of dropped out in between because of internet issues. But will any of these different options that you have not work if you're trying to take your capacity into consideration?
Sorry, if I'm using the...
If you need to take capacity into consideration, or any one of these options that you've talked about become a non-option, or all of them could be massaged to work with capacity?
So I would say that this one is probably the one that fits the most with capacity, because the load and the utilization already take that into account when we are computing them. Now, in the imbalance, the value that we are using, we're already taking into account the capacity as well. I probably need to run more tests to see exactly.
I think we're running
maybe this one should not be that much difficult. Yeah, just one last thing, especially because I think that because of this often the same times that is pulled, I will probably have to use somewhere the utilization, and with utilization, the capacity can be used to scale the utilization. Oh no, the utilization is already scaled by capacity, so that would be maybe a way. I think we are done. Maybe we can continue on the chat if needed. But yeah, thanks everybody for your input. I will read more deeply the chat. I haven't been able to read all the comments.
Thank you very much, Vincent.
Yeah.
Next, we have Valentin, who's going to talk about pneumotopology. Valentin, you should have presenter powers right now.
Okay, let's see about that. Yeah, looks all good. Should I just jump straight through, or do we have another break?
No, you're up. The break's
Okay.
after yours.
Right, okay, thanks. So, another year, another topology talk. I already had one last year, and I'll try to briefly summarize it and try to give some closure. And then we'll move on to NUMA topologies this time around. So last year, I rambled about building the MC scale domain differently on some systems. So like the level that represents CPUs that share a last level cache. The thing is, the experiment that I used, or like the platform that I used with the experiment that I run on that machine, it's pretty unique. I was expecting to be able to reproduce my experiments and my findings on other systems, but it's been a year already, and it's still the only machine that I found that behaved like that. So I'm willing to put in the time and effort, but I'd like to find some other systems where that would be useful first, especially since SunDirects is kind of becoming outdated by now. So interestingly, the PowerPC guys have a topology series going on right now, and from what I understood, they are describing something, let's say, closely related. So maybe this will resurface, but yeah, for now, what I talked about last year, I'm not forgetting about it, but it's in the freezer for now. This year, instead, I'm going to be talking about NUMA topologies. And one thing I need to talk about is what I call NUMA diameter. So I'm directly borrowing this from network on chip speak. And essentially, it's what is the longest path you're going to have to take to connect any two nodes. So the topology on the left is directly taken from that interesting paper, A Decade of Reset Cores. So that's an oldish AMD bolt dollar. And that is diameter 2 because you have at most 2 hops to connect any two nodes. So for instance, if you look at node 0 and node 3, you have to go through 2 hops to connect these, and that's the worst case. And actually, that seems to be the worst case for all of the systems running Linux. I did a bit of investigation on the x86 side, and diameter 2 is always the maximum I found. And that was also true for ARM64 until recently, where the topology on the right was kind of thrown at me. And that doesn't work very well with the way we build our topology data structures at the moment. So we can already have an objection on that topology, and you can ask, how much money are they really saving by not having some sort of link between node 0 and node 3? I don't have the answer to that. All I can say it's a system out there that exists and that's trying to run Linux, and it kind of falls over. So I've sent about a week ago an RFC on the list. There's no code. It's not a patch, just a wall of text that goes through that topology on the right and tries to explain what goes wrong in detail. And what I'm going to do today is try and do the same with a topology that perhaps makes a bit more sense. So it's still theoretical in that this topology here is in C shape on the right is the only one I've been able to get my hands on that has a diameter of 3 and runs Linux. but I've never found a system that looks like this. On paper, it looks a bit more sane. It's a 6-node mesh. So you have 6 nodes, and to keep things simple, we can say we have 1 CPU per node. So if we look at the topology that we build for this, so we're going to have just our NUMA domains, right? So they're directly going to represent the CPUs that you can reach in a given number of hops. So usually for NUMA, we talk about distances, but we can just translate that to hops to make things simpler, right? So if you look at CPU 0's point of view, its domain hierarchy, we will start with just the local node, which will be CPU 0. And then if we go one level higher, the domain will be all the CPUs that you can reach within one hop. So that still includes the local node, but also outreaches to CPU 1 and 5, and so on for 2 and 3 hops. So those are the scale domains we really get of a system like this. It's quite easy to simulate something like that with QEMU. The problem is when you look at the scale groups. So still focusing on CPU 0, those are the scale groups that you get for the domain that represents all CPUs that are 2 hops away from CPU 0. So that should be all CPUs except CPU 3, right, which is in the corner, and that takes 3 hops to connect it. But what happens is we actually get 2 groups that include CPU 3. So despite being in a domain that's supposed to represent all CPUs 2 hops away, our groups cover CPUs, actually in this case, the only CPU that is 3 hops away, which I suppose is obvious to say is an incorrect representation. So your system is not going to crash. The scheduler will not catch fire. You'll still be able to boot and run whatever you want. The problem is whenever you're going to have to make decisions based on this domain hierarchy, you're going to make usually the wrong decision, or you're going to break most of the heuristics that we have. So if you look at load balance, for instance, we start from the lower domains and we try to go up if we see that we still have an imbalance to solve. So when we are trying to balance at a domain that's supposed to represent all the CPUs that are 2 hops away, at most 2 hops away, we're actually going to be influenced by what is running on the nodes that are further away than this, right? So from node 3 in this case. So the thing is, and the tricky thing with that is, it is mostly a theoretical problem. So there is one machine out there that I have my hands on that breaks this. The thing is, the topology is peculiar, to say the least. It's not difficult to come up with other topologies that are going to break this. As soon as you have a diameter greater than 3, you're going to have this problem. The thing is, and that's where I'd be interested in getting input, is how likely are we to see systems like this show up running Linux? And the reason for that is, as far as I can tell, it's not an easy thing to fix. It pretty much requires going in there and overhauling the way we build, at least overlapping scale groups, so scale groups for NUMA domains. And it's not something, to be honest, it's not something I would be looking forward to be doing. So at the very least, what we can consider is, well, documenting this, because it's not a limitation that is documented anywhere, and perhaps have an explicit warning when you put up, say, oh, we detected that you have a system that has a diameter of 3, that's not supported. And otherwise, yeah, so I have this RFC on the list. Feel free to pitch in if you have any comments. I sort of expect, I kind of expect no one to come in and reply to that, because that diameter of 3 seems very peculiar. But that's the state of things, and that's an actual limitation that we probably need to document somewhere if someone wants to build fancier systems running Linux. And that's actually all I have.
So those really big NUMA systems that have backplanes, I'd have to look up the topology for them, but don't those qualify for this?
So probably. The thing is, so I'm doing like a shortcut by talking about hops. From what I can tell in the actual topology code, what matters is how many unique distance values you have, because that's sort of considered as hops. It might always be true. It might just be that, yeah, like your backplane is a bit more expensive than a direct link. But that will still, in terms of like construction, that would be like having 2 hops or 2 different hops. So as long as you can have 3 or 4 unique distance values, that thing that I call diameter 3, you're probably going to hit this. The thing is, you should be getting a warning at boot up with sked debug enabled, because it's going to check that the sked groups extend outside of the sked domain span.
Okay, so
yeah, if you can check on real hardware, I'd be overjoyed.
So we already have the warning if you boot with sked debug.
Aha, okay.
No,
So
that's the question.
So on, which one is it? That thing here on the right. That's initially that's all I got. Like I get this cryptic warning about sked groups extending outside of the sked domain span, and when I dug into it, I realized that this was the whole construction thing that was falling apart when you exceed diameter 2.
Okay. Because you can view that as 2 clusters. The cluster. No, maybe not. Yes, yeah, I'll have to look up if I still have the topology information for those big NUMA machines. Rick, do you still have that? I think when we did Auto NUMA, Rick added some of the backplane stuff in.
So yeah,
I played around with a few different topologies there. I think the largest ones that I played around with were 8 nodes, and I think one of the either Hitachi or Fujitsu systems might have had diameter 3, but I don't remember for sure.
Okay, okay, at least write this down. But yeah, so if you have like names of systems, or even if just you remember about systems that look like this, and if you can just either ping me or reply to the RFC that I sent, that'd be highly appreciated. So I can try and see if there's really cause to try and spend time supporting this in some way.
Stupid question here. What about these mesh architectures you keep hearing about? Would they also have some of these really long paths between nodes, or they all come within diameter 2?
So you mean like a mesh like this?
Yeah.
Yeah, so fairly quickly you can hit diameter 3 with nodes like this. And
are there any out there running Linux?
Not that I'm aware. This one is completely theoretical. That's, I mean, of this size with diameter 3, because I've really been struggling to find systems out there. So I try to look for like complex looking things. That's why I looked into the one from a decade of reset course, but that's still diameter 3.
So from what I understand, most of the mesh stuff is for chiplet interconnects, fabrics. And it depends on how you connect the memory nodes to that and how the topology, NUMA topology then ends up looking. So most of the mesh is actually connecting chiplets, not NUMA nodes as such. Yeah.
Some of those meshes, the chiplets have separate memory controllers though. So you might hit it.
Yeah, I don't know.
Yeah, I need to have a dig through some of ours.
Exactly.
Valentin, if I remember correctly, the issue manifested itself when we played with this, that you don't have all the unique distances in the first row of the distance table.
That one is another problem.
Okay.
I mean, we have time, so I can, I don't know, I could spend some time on this. Yeah, there's also problems in the way we figure out those unique distances. And it's not necessarily clear what are the rules you have to respect. So yes, you need to have all of the unique distances in the first line of the table, but it's very easy to take a topology that works and just do some renumbering of the nodes in there, not change the actual topology, and you no longer have this property. So we can think of other ways of doing it. The reason we are doing with the current approach is just because we would move from n squared to n cubed. If we had some form of dictionary in there, we could keep it n squared. I think I have a preliminary patch somewhere that does it, just with a bitmap, because I think in the ACPR spec it's supposed to be like the distance value is on 8 bits, so you can use a bitmap for that. But it's another problem that same topology has. It's just, yeah, it has more than one.
But at least it's easy to play with all of those things in QEMU, right? So you don't have to have the actual machine, so you can test it. You can see how the code behaves, like this.
Yeah. So for instance, this C-shape thing, I have the QEMU contention in how to simulate this in the RFC. And if that's it, I guess we can have an extended break, unless someone else has any other thing to pitch in. Right. Well, thanks everyone for participating and hearing to what I had to say.
Thank you, Valentin. We will be back at 10 minutes past the hour, so it's a 20-minute break. I guess people are starting to come back now, slowly. Are you online?
Yeah, I'm online.
Okay, great. So I'm going to hand you presenter right now, and we'll start in a couple of minutes.
Yep. Okay.
Okay, so this next topic is about the thing that was latency nice. It's a big group here. We have we have Chris, Patrick. Who else do we have? We have Dietmar and Parth. I think I got everybody.
Yep.
Is everybody around?
Yes, I'm around the web.
Perfect. So why don't you get going? And then, guys, when you're ready for me to switch presenter to Patrick, let me know and I'll do that.
Yeah, thanks. Yep. Hi. I'm Hi from Google, working on production kernel. So first, you might be this might be a bit unexpected because it wasn't in the description. That's because this talk was merged into the latency nice talk, and you don't see the descriptions there. but you may find it fit nicely and warms up you to the next latency NAS talk, because many of the issues are related. We plan to finish the first. We plan to first finish the 2 presentations and leave big discussions at the end. This talk is about our workload and the problem and thoughts. I don't have a specific solution. It's about discussion. Okay, let's flip the slides. Oh, it has delay. Okay. Okay, so it's back. So observation is that many applications are latency sensitive, but they're not specialized enough to fit regular RT or SCAD deadline, and CFS being their only practical choice. And at least for our workload, it's a wake-up load balancing that keeping them happy, because we have quite a few cases. We control the load and keep and with wake-up load balancing, we have 1 thread on each CPU. Then everybody's happy. So as soon as some thread are sharing CPU, then we have the round-robin latency. That's like 10 millisecond level, jump from microsecond level to 10 millisecond level. Then we can have a problem. So there's a periodic or new idle balancing, but they are not fast enough. For our workload, usually we want to search more and spread more. But in the next talk, you will find that for the latency NAS case, some of the usage case, they actually want to search less to reduce the latency. That's because if you spread, you migrate frequently, there's a idle CPU search cost and the migration cost, both reflected in the cache line bouncing. So you can see there's, sorry, you can see there's some major feature creep there. So select IO sibling kind of becomes the soft RT class. It's very important compared to the code size. So any change can trigger problems. I have a problem going to the next slide.
Did you get disconnected by any chance? For some reason, you had lost presenter.
No, I don't see that. Strange. Okay, so that's not an ideal solution, because like I said, even small change can reshuffle application performance metrics. And the problem is if you get some improvements and some regressions, the regressions get more attention. Sometimes we have to reward the new upstream behavior back to the old behavior, even the change makes sense. So that affects how closely we can track upstream updates. So another problem is this all jammed into like different goals and factors all jammed into the same path. You can make only one decision, which is that's the CPU. So in the table, you can see kind of every factor is related to every goal. So it's hard to reconcile. Then I will describe a few problems we encountered in this code pass. So the first one is the order of search. We had a major regression when Upstream went from the search from CPU 0 to search from most of the time is a weaker CPU because of the cache locality. The search from CPU 0 is actually a form of like a load consolidation, like merging the load, because only so if you have short time slice that's idle on CPU 0, then it's likely to squeeze another task. So if you search like uniformly distributed, it's the upside is it's better distributes the load, but the downside is the cache locality can go down. And at one time, there's if you have two threads waking up each other, so they can do a kind of walk through all the CPUs. So rotate all the CPUs because A wake up B when B wakes up A. So you have this so A CPU become busy, then you search the next CPU. So you can have this kind of walk. And the recent Upstream has added some this recently used CPU that should fix the problem. But I think there should still some cache locality differences. Maybe we can still improve. But the next one is wake up fine. So it's also related to select idle symphony. We had problems with if we enable this WA idle to many tasks migrated to the CPU 0. CPU 0 get overloaded. That's a specific case because we have too many interrupts on CPU 0. Another thing, most of these are really RQ related. So it's a hard decision about if we want to consider hard or soft RQ CPU to be idle. They are kind of different from threads because we want them to finish quickly. But sometimes they don't. Like this networks of RQ, they can run for a long time. But at the same time, they don't have load tracking as others, not so detailed. But interesting is the timer interrupts, because if you want to wake up fine to timer interrupts, you may find it's actually not required because they're scheduled by the thread. So if we move the thread, it actually moves with the thread. Non-interrupt related issue is that we have tried several times to get wake up fine across NUMA, but each time we get some regressions. The max range of search can also be a problem. Like we recently had a problem with the AMD CCX. They have these 4 to 8 core NUMA domains. We found that we can't efficiently use all the CPUs. That's because if you have a very big CPU socket, the task also scales up. You have run big tasks with many threads, and if the load is not very, it's very dynamic, when the load shifts, you can have like a trace. There can be a big host. With most of the CPUs idle can be utilized. The other side of the problem is if you move across NUMA so frequently, you're going to have lots of overheads. Early stage termination is a new addition to this code pass. We found it works well if we have like a more uniform task distribution. That means all CFS threads can move freely. But if we have CPU sets or we have the RT thread, then it can be less accurate. So this is the last slide. I want to talk how can we improve? So we can improve keep improving it in small steps. It's relatively easy to just do customized code for specific cases, but it's difficult to generalize or upstream. Then that's we could do customized tuning. If for most problem, we also try to find a universal solution first. But I think this problem has already proven to be very complex. So maybe we customize citing, customized tuning with latency is nice and it's a newly evolved form. We actually simplifies it. So that will be covered in the next talk. Even more longer term, so maybe we can explicitly support them. I think there's a population of server-side applications that are less sensitive. They actually can be described nicely with deadline. It's just that their deadline is like maybe half a second, but they're indeed latency sensitive. We could explicitly support them with a new or existing SCAD class. Like one thing we can get out of this is if we can enforce deadline, then like we spread into idle CPU less critical because they can get priority. Even the high priority thread share a CPU with the low priority thread. So so why can't we use the existing RT classes? That's because some generic features are still expected for this kind of applications. Like they have many threads. You can, we generally can't just admission control. We should be able to handle both, like within spec or open subscriptions. And there's other things we expect from CFS. So that might be a hard problem. So that concludes my talk. So we can move on to the next one. Then we can have discussions. Thanks.
Patrick, you want to talk first?
Patrick, you're muted.
Good point. Okay. So this is a follow-up of the discussion that we started at OSPM early this year. And so the old problem that has been nicely introduced by Xi also from the Google standpoint is that we know that we have different classes of workloads that can benefit from some kind of dynamically tuned wake-up path. And dynamically tuned because we know that the different tasks can have different requirements, or the same task can change the requirements at runtime. And in general, broadly speaking, what we see is that we have the needs either to reduce the wake-up latency, because there are some latency-sensitive tasks that needs to find the CPU and start as soon as possible, or they rather like to spend a little bit more time to find the best CPU to allocate the task there. And they are generally not latency-sensitive tasks or called latency-tolerant tasks. And so far, the story is that we collected use case from different parties, mainly Oracle, IBM, ARM as a use case, and Google we discovered today has plenty of other similar use cases. And the problem is that at OSPM, it was a little bit confusing. Let's say the presentation of this case, it was not really easy to understand if these use cases have similarities and if we can try to find a common solutions that satisfy all these different use cases. One of the problems that Xi also called it out before, I think, is that it's very easy if you keep adding heuristics that at a certain point you have heuristic step into each other. So you can really find them working nicely together. And so the idea after OSPM has been to start working on the requirements, as it has been suggested at OSPM by Thomas, actually. And what we did is come up with a template, so a general structure to try to and use it to collect the requirement of the different use cases, with the goal of potentially trying to surface and see if there are commonalities across these different use cases, and possibly come up with a unified interface, or convince ourselves that we really need the different interfaces to tune these things. So the result is posted in that thread that is linked in the reference number 1 in this slide. That's where the template is presented on LKML, and this table is trying to resume and to capture at least the 4 use cases that we discussed, we partially discussed previously at OSPM. In this table, there are less details than what you can find on the mailing list, but we are trying to capture the major points. And now what we do is basically each one of the use case owner, let's say, that will introduce a little bit what is, or resume what is the goal of the use case. Then the goal of the discussion is a follow-up slide where we have a few questions that we would like to address during this, the follow-up discussion. So the first use case is from Chris, skip idle CPUs, and please.
Yeah, so this is actually very similar to what she was looking at. The observation is that you have this large LLC domain, and what we have is we have a policy on wake up, and this policy is being applied to all tasks across the board. And I think the observation was that some tasks could require special treatment, specifically based on latency requirements. And so the idea was, instead of just generically treating all tasks the same at wake up time, let's add some administrative knowledge about the task, which would allow us to handle this better. So all this is basically skipping the large idle CPU search for tasks which are incredibly latency sensitive. Yeah, that's fine. So what we do have, though, and what I do want to say here is, we originally started out with the latency nice mapping, and I'm actually happy with that, because what we're talking about here shouldn't be how does any one particular use case use something, as much as how do we describe the latency characteristics of the task, and nice does seem to capture that. So, next.
Okay, Dietmar is for
yeah. Okay, so that's another use case which could actually live side by side with the skip idle CPUs for SMT systems. That's the skipping the energy aware path, which essentially creates a lot of latency for those tasks. This wake up path is only used on asymmetric CPU capacities, like big little systems, when you have an energy model applied. And the only thing we want to do for a specific task, normally all the tasks should go through the energy aware wake up path to find the most energy efficient placement of this task, considering the task landscape at this moment. But there are tasks in an Android system, for instance, which essentially don't want to have this huge latency related to this. So we want to route them through the select idle sibling path. And couple of months ago, we started to have like our own select idle capacity functionality there. To achieve this, we could use the latency nice thing. It actually boils down to the fact that we only need a binary switch. So we say the default task is has a latency nice, or whatever we call it, of 0. Then obviously everything goes energy aware. If it's 1, then we consider this task latency sensitive, and we route this through select idle sibling, which is faster. Maybe one thing to add, this scenario or this thing is already used in existing Android systems, and it's still there. The name there for this feature is prefer idle. And yeah, we have this there as a task group interface, but that's another question. So we could also live with a per task interface. That's
and so Dietmar, in your use case, for example, you're looking for an idle CPU. if possible? I mean, you prefer to go through all the CPU, finding an idle CPU?
Yeah, that would be select idle sibling or select idle capacity, yes.
Yeah. Yeah, it's just for me that, I mean, for the negative value, you're looking for, I would say, something a bit opposite to Chris, where for Chris, with negative value, you want to minimize its search loop. That,
Well, okay, so we essentially what's important, and we probably talk about this later as well, those two use cases will never exist in one system because like I said, this is only for capacity aware or energy aware scheduling on asymmetric capacity systems, which we will never go through the normal select idle system call. And that's why when we talk about like, can this combined interface, let's call it latency nice, even though we don't want to, if this exists in the system, both systems could use the same kind of tuning interface, and this is what we try to figure out here. If those use cases can coexist with each other.
So how do you document that?
Yeah, that's my point. I mean, if you're an application and you say, okay, I want a negative latency nice value, in fact, the behavior will be, I would say, almost the opposite. That's my main worry.
By negative latency nice, I mean the task is latency sensitive, and it maps into this specific ES use case by using the faster wake-up path. So in a sense, it's very similar to Chris's use case. He also wants to use less time in wake-up.
How many of the things here are actually policy, and how many are just the side effects of the unfortunate linear search?
Well, so the linear search is policy, right? The policy is to try to make sure there are no idle CPUs if there's work to be done. And that's a perfectly reasonable policy as a default. I think the observation is, in the case of knowledge about tasks, like their sensitivity to latency, you can have other policies. And so the idea here is there a parameter which describes the latency sensitivity, and then the five of us can go off and do interesting things with tasks that are either latency sensitive or latency tolerant. And what we're arguing about here is just, does it make sense to have a per task attribute describing the latency requirements of the task, and can you do useful stuff with it, right? And I think the answer is yes.
Yeah, I would just like to call out that this mapping example here, which is quite clearly referring to latency nice, is not to be considered like a proposal right now. This is just to resume what we started the discussion from in OSPM. And here the goal is really to, we will come to some questions after the table presentation, but it's really to try to understand if the use cases make sense to begin with, and then eventually if they can be combined to be described with a unified API. But we are not really proposing to use that API or that mapping.
No, yeah, that clearly my point, because for me, looking at that, the two first use cases look like they are a bit opposite in the policy, in the internal policy. I agree that they want to achieve the same use case, being as fast as possible. But I mean, I'm not sure that it's possible to say. I mean, if we take the Dietmar, so his goal is to say in ES, if we have a negative latency, we fall back to the select idle sibling. But in select idle sibling, if we follow Chris' policy, we will skip searching for an idle.
Sorry, that's why I try to emphasize this. Since energy aware only makes sense on asymmetric capacity systems, we have to be careful. Select idle sibling has different sub-functions, where one of this sub-function is select idle capacity, which is always used on those asymmetric CPU capacity systems. We are not talking about select idle CPU or select idle core, which are the function where Chris's use case actually is in. So we will not go into this problem.
Yeah, but for me, that's a problem from a interface point of view, because in the two cases, you fall back to two opposite behavior, and how do you decide? I mean, if
No,
both have to be enabled simultaneously.
Well, because it's based on the tasks, though, right? The tasks that would want to skip in one case get handled differently by the other case, and that's based on their description of their sensitivity to latency. Yes, Dietmar, did I say that right?
Yeah. So yeah, I don't. So for me, those two use cases can never exist in one runtime. Even though we use the same kind of interface to specify latency sensitivity, we would not actually go through those two use cases in one running system.
Yeah, that's a very valid point, that they probably don't exist together. However, if they should exist together, I think that the behavior is still coherent, because if you go in the negative space, you are more latency sensitive. And so it means that you skip energy aware wake up, you go for select idle siblings, and in this part, you are in this part, and you, in the negative side, you reduce the number of CPUs to search. And eventually you stop in one active CPU and run there because you are latency sensitive. So there is still coherence between these two use cases.
So in this case, you mean that it's valid for the Dietmar use case to finish, to skipping, I mean, it's...
Probably yes. I mean, I think it is.
No,
I mean,
that's my point. Yeah, that's my point. I mean, we have to
it's an additional
have a global behavior.
Yeah, exactly. It's an additional feature. So if you don't have this feature here, you will just keep energy aware wake up part. You go for select idle sibling, you search all the CPUs. But if you are very negative, you reduce the number of CPU to search, and you terminate quite before a select idle sibling in one of the active CPUs eventually. Yeah. So there is still consistency if they should work together, but we think they are not working together.
Yeah, but what you're saying is that we will enable or disable the feature on a platform basis. That's not something we are usually trying to do, to have different configuration, because you're just having more and more configuration to test.
Yeah, but I mean, if we are on an asymmetric CPU capacity, this will be figured out when the system starts up. And if this is the case, we essentially block select idle CPU and select idle core and select idle SMT, and we always go select idle capacity, which is a different path. So I think this, if the system comes up and during runtime it figures out I'm in this kind of category, it would make sense. I mean, how would you ever otherwise use a common tuning interface for different use cases?
The key here is we're trying to describe the nature of the task. We're not actually trying to map anything we're doing to the use case. We're just trying to say, this describes the sensitivity of the task, and various use cases can do different things with that. And as long as they're consistent, and I get that's the question, and we're trying to analyze that, but as long as they're consistent, it's okay, right?
So I'm not really, I agree that all these use cases are probably trying to do the same from an interface point of view. What I'm worried about is that then you can have an opposite behavior internally, which for me is a problem.
That's exactly what we want to avoid and convince ourselves that is not the case. And if there is conflicting behaviors, it should be possible only if two use cases are, for whatever reason, not possible on the same platform. And regarding disabling things, already now, if you boot on a symmetric system, the EAS part is disabled by default at boot time.
So Patrick, I don't agree with the notion that if you have diverging behavior on the same platform, it should not be possible on the same platform. I don't think I agree with that. It should just not be possible, period. Because if it is possible, you cannot document it. How do I know at what point in time I want which behavior? So at that point in time, you need two new interfaces, not one interface trying to do it all.
True. So I misspelled by mind. Let's say that it's not possible with a unified knob. It will be very hard or not possible. You will have to fall back possibly to different knobs to capture the different behavior. But still, we have to convince ourselves that if in a same system you have two behaviors enabled, you never have like a behavior stepping up in each other. So one behavior working against the other. And that's why it's very compelling, the export, to try to see if we can map everything with one single unified knob.
Well, but you can't say that today anyway, right? You still have one knob stamping on another one, for one reason or the other.
Well, not really. The exercise that we are doing here is try to see if you can find a coherent setup that works in all the use cases.
But can you guarantee that already today? And I don't think you can.
Well, that's the scope of this discussion, and try to convince ourselves those initial proposed mapping, if they kind of make sense. But we have other. Can we just close the table review and then we jump to the question? Yeah. So if we lost a part somewhere, you still around? Maybe if
yes,
well, okay, cool. We can go with yours.
So this use case is basically regarding task packing, and currently what we are doing for each task wake up is find an idle core first. So we prefer an idle core if there is any in LLC domain, and try to wake up a task on any of the CPU in an idle core. But is it energy efficient? So it may not be for some of the tasks, like some small background noisy tasks, which are latency tolerant, which don't care for the latency much. And it doesn't make sense to wake up an idle core for that, and rather use a busier core for waking up such type of task. And this will effectively save energy, which will result in saving power budget and boosting our turbo frequency and all that stuff. So what I want here is that if we have a new wake up path for this latency tolerant task, which are also small background noisy tasks, so we will have furthermore classification like whether they are small or not in utilization and all, and they are latency tolerant. Then we can use a separate path rather than the select idle sibling path. We can use separate path for selecting a busier core and put this kind of task on a busier core. And there will be certain thresholds. If this is basically regarding the TurboScad patches that I posted. So there are certain thresholds for which we select that whether a core is busy and what is the capacity left in that core. But the idea here is to expand the search beyond LLC domain for latency tolerant tasks. And latency nice or whatever interface we are looking for suits best for this kind of behavior where we want to do task packing. But it all boils down currently to a binary interface where we want only whether a task is latency nice or latency sensitive or latency tolerant. And that's where we say that if a task is marked with 1 or if it's latency tolerance, then use a new code path to wake up on busier core. But we could also have a range, just like we have in skip idle CPUs. We can have range to limit the search for finding a busier core beyond LLC domain. So the skip idle CPUs will limit the scope within the LLC domain, and here we can go beyond LLC domain. But how much that can be controlled with the latency nice range, which will be above 0 value for the latency tolerant task. This is the basic idea behind task packing. Any question around it?
Okay, so I'll just go before going with my use case. I just want to call out that we added some coloring here to represent some ideas, and the point is that these first 3 use cases, they all refer to CPU selection wake up path, and specifically the first one is tuning whatever is already there in mainline. The second one is still for latency sensitive task optimization and is about skipping something which is already in mainline. In the third use case, we are instead talking about adding a new wake up path possibly to take in certain specific consideration. And we adding also these searching behind the last level cache domain, which is somehow pairing with this use case eventually, because here is we are skipping or reducing the number of CPU in a LLC. In this case, we are going further behind the LLC. The last use case is an example of a possible use case where we work after we selected a CPU and we want to allocate that or want to select a task to run on a CPU. And then in that case, we can still try to play and optimize for latency sensitive tasks, or mainly try to make latency tolerant tasks not noisy for latency sensitive tasks. And in this use case, what we would like to try to do is see if we can avoid that a latency tolerant task working up in a CPU will preempt the current running task if it's a latency sensitive task. There are already heuristics in the scheduler to play with these kind of things, but they are mainly based around the priority of a task, which is good. And the priority of the task defines the wake-up granularity of a task, and it also impacts the bandwidth, the CPU bandwidth that the task will get. But the decision whether to preempt or not is driven by this equation. And the idea is that if we work on the left side of this equation instead of the right side, maybe we can try to do something different. So the right side will work on the priority of the task. The left side can be hooked into the latency nice or latency properties of the task. And again, we can try to find out a linear mapping where we transform this hard-coded behavior or heuristic, which is now in the scheduler, into something which is more task-specific, or eventually also task group specific. So given all these use cases, the main question that we had for these remaining 15 minutes and the main discussion points that we had are those, I think, two. This is mainly like a starting point for the discussion on the mailing list eventually, which is, the first one is, are the different use cases work, can the different use cases work together? So it's more or less the discussion that we had before. There are use cases that are complementary and then they will never work together or not. The second question is if we really have a case for search more CPU. Chris' use case is about reducing the number of CPU that we search. We really want to know if there is a use case for searching more CPUs behind the last level cache, or if we think that it's just misconfiguration of the scheduling domains in general. And then some other minor question, mostly what has to be like the unified interface that we can try to use, if a single node can work or not. So I don't want to spend all the time. We can start from the first question if there are opinions or feedbacks in general.
Patrick, if you go back to the table,
yeah,
I think the issue here is we can't just put, like for instance, task packing and skip idle CPUs. If they both use the positive latency tolerant values, then obviously those two wake up paths, even though the third one doesn't exist yet. But I mean, then we would probably have this issue that the change in behavior, or the tweaking in behavior it might be different in skip idle CPUs than task packing. Whereas I would say this is not really a problem of this interface, but it would be a problem when we essentially integrate one day the task packing wake up path, because it doesn't exist yet. So we can't possibly, like, I think this task packing feature is also enabled when the system sees the first task, which is probably latency tolerant. And then this feature is enabled. That means the wake-up path becomes active, and it probably steers task away from the skip idle CPUs. So I think we can't just use the latency nice values to control the wake-up path. That might be an issue. Whereas look, with skip idle CPUs, skip energy aware, we were lucky because they can never run in one system. But I think in one system, but skip idle CPUs and task packing probably could. Because both of them are in the area of CPU selection. I think with your runtime thing is completely orthogonal to the CPU selection. So I think this is easier to handle than having two use cases which can be active at the same time in one system.
So if I understand it correctly, what you are saying is that if we go, for example, with this mapping and we are positive, so we are latency tolerant, we are a latency tolerant task, and we have all these three things together. For a latency tolerant task, not only will search all the LLC CPUs, but we also try to pack that task into a CPU which is quite busy, and that can be something not wanted by the user or difficult to explain to the user.
It's probably not what we want. That's definitely not what we want. But that's a question of integrating this task packing feature into the existing code, which we haven't done yet. So it can't be this that the system sees the first latency tolerant task, it enables turbo shed or task packing, how it's called, and then obviously the skip idle CPU stuff completely hidden.
Yeah.
But this is not an problem of this interface. It's more a problem of how to enable those different features in common runtime environment.
One thing, if I can add, is that talking about the interface, can it make sense, even if we have, let's say that we can agree that we can have a unified knob, can still have sense to have some additional features enable flag that are system-wide, where you can say, okay, in this specific system, I want to enable task packing on top of skip idle CPUs, so that when you are in the positive range, you know that it will take this part, so you will search all the CPU, and you will also try to pack or not if you disable this specific feature in a system-wide way, or maybe in a task-specific way, using a flag only for that specific feature.
Yeah, I think task packing, when it will go mainline, then it can't actually be turned on by just seeing a latency-tolerant task, because then the whole thing doesn't work together. It's probably right now implemented this way by path, but it doesn't have to be this way, I guess, when I remember the patch set correctly.
Part, you're muted, probably. We can't hear you.
Or we can't hear you,
yeah.
Unfortunately. Yeah. Try again. Yeah, we're not picking you up, sorry.
Okay, well, so while we wait apart,
I think I'm audible now. So yes, it won't come into picture. The task packing won't come into picture unless we say that the task is small and background task. But the only way to tell that the task is background is by the means of saying that it is latency tolerant. Small can be determined by looking at the utilization of a task or looking at the previous history of utilization of the task. So yeah, there are several switch cases after crossing which only we will do task packing.
But still, like for instance, like the energy aware thing, it actually works together with a normal wake-up pass in select idle sipl, because it requires a lot of crazy features like asymmetric CPU capacity, which is detected dynamically when the system comes up. It requires an energy model. The complexity of the energy model can't be big enough. We do need a specific frequency governor, etc. So, and all those points, they essentially make sure that we never then work in select idle siblings. Whereas between turbo scheduling, task packing, and the normal select idle sibling thing, I'm not so sure. Task packing should be enabled through some other means than just your utilization of the task and the latency tolerant. Otherwise, we have to make sure that those positive numbers in latency tolerant, in the latency nice range, are only for task packing and not for skip idle CPUs. So we only consider everybody as 0 is default, and then skip idle CPUs only uses negative, so select latency nice values, and you use latency tolerant. But this mapping of functionality of the Linux scheduler underneath this API, it has to be specified somehow and obviously understood by people. And then it comes to the question which came up before, it has to be documented as well.
Right.
It's probably true that in principle, if you are latency tolerant, you can also accept to pack. Or do we have examples where we say, okay, you are latency tolerant, but you don't want to pack a task?
Yeah, if the utilization of the task is too big. Like Path just said, there are two things which have to be.
Okay, because you will destroy the latency of the already scheduled tasks there.
Yeah, but not every, if like I said, if task packing is enabled by latency tolerant and utilization, I think not every system wants to pack if it sees small tasks and they are latency tolerant. That's not really clear to me.
So in your use cases, part, do you usually also set a low priority for tasks that are considered latency tolerant, or priorities never touch it?
No, yeah, it should be latency tolerant, and then only we do task packing.
Sorry, you don't tune priorities? Because I was trying to
Yeah,
understand
yeah.
if these use case should be extended. Say, it's not just how much you are latency sensitive or tolerant, but this should be combined with, okay, it's also a low priority task. If it's a low priority task which is latency tolerant, then I go and pack it. Otherwise, it doesn't make sense because it will destroy the latency of similar priority tasks.
Right. Right.
So just because we can keep talking about this topic for a while to make some little progress, if you go down to the next slide, I think I can answer one question, which was, do we have a case for search less versus more?
Yeah.
Rick mentioned in the chat that they have seen a case when they have lots of cores in a CPU. Sometimes select idle sibling ends up placing a woken up task on a busy CPU. So that clearly seems like a case where we want to search more CPUs.
Yeah, I think C also has a similar case, isn't it? Like you want to search farther above the LLC.
But I think Rick's case is still like within one LLC. It's just like the logic inside select idle sibling prevents him to essentially search all the LLC CPUs, and this latency tolerant thing could essentially make sure for those tasks we skip the logic, which would otherwise.
Yeah, I think that's his prop. Maybe that's the new addition. That might be SS.
With
it's called prop.
on and off, and both perform worse than the other in certain conditions with the same workload. So ideally, what you would want is to always find an idle CPU, but search fewer things.
Yeah, it also depends on the like what kind of latency you want. If you want like if your latency tail is like 10 milliseconds, then the problem is most likely not finding idle CPUs. If you have priority and you have like 50 microsecond latency, then that could be a search and migration cost. So that's what I think.
So I guess my question here is, what is our next step?
Yeah, I'm also sorry. Okay, I'm also interested in like more parameters. Yeah, so that's all.
So you are proposing to go for an interface that adds multiple parameters, one per every use case, you're saying?
I'd be interested. I don't have any solid idea, but I'd be interested in like more than one value.
So
Yeah.
it seems to
Something
me,
like
it seems to me the question here is, we could obviously create any number of useful policies and controllers. We could create any number of inputs that we shove into each of those individual controllers. Or is there value in saying, knowing the latency about the tasks is useful even for future decisions and policies and controllers, right? It's like, I now know something that only the admin knew about this task. And I can use that to do useful stuff. And I need some way to communicate that I know about its latency sensitivity. So I would argue, let's have something that describes the task and then let these individual controllers, policies, whatever, map that to their behavior, as opposed to just as opposed to just inventing any number of integers, right? We'll just pass a whole giant arrays of integers in and we can do anything, right? I mean, let's describe the nature of the task and let the controllers do something smart with it.
People also say that it's very hard for the user to know what this means, but like, look at today's nice values. What do people know about nice values and how the nice values actually change the behavior in the runtime? I mean,
or worse, they set RT policies, right? They choose RT and they have no idea how to set up the system, and then you've got all this stuff as just RT and nobody knows.
So I think this we can't prevent with this interface, but like Chris said, I mean, do we want a common interface for the same kind of functionality or not? I mean, the implementation behind it is it's very similar, and the per task interface already exists. So there's not a lot of work. I guess it's just like doing the step and say we can have latency nice and we can describe it correctly, and it actually works exactly as good as bad as the, for instance, the nice interface.
Okay, so just to close, we will follow up on the mailing list with those questions in the thread that we have, and hopefully we'll have a discussion there, getting to some conclusions. Thank you, everybody.
Thank you very much. This was actually a fantastic discussion.
Yeah, thank you.
Thank you.
We have a break now. We should be back at 10 past the hour. Hey, Valentine.
Yep.
Okay, you're around. And we have a good chunk of people back again. And it's time for our next talk, which is going to talk about proxy execution. Valentine, once again, I'm handing over control to you.
Okay.
Or you might want to get rid of that old result.
Yeah, how do I do that?
There should be a garbage can.
Yeah, okay, thank you. I'll just wait for my clock to say it's 10 and then I'll start. Okay, so proxy execution. For those who are not really familiar with it, it's going to be priority inheritance, hopefully in a better way. So yeah, I'm going to hopefully briefly recap what proxy execution is about, have a status update, what's been going on, and hopefully have some discussion on what I consider to be prickly points, but we'll see when we get there. So first of all, why do I care about proxy execution or priority inheritance? So proxy execution, as I said, hopes to be a better priority inheritance scheme than what we currently have in Linux. And it so happens that we ARM folks have something called Big Little, and we have inheritance problems of our own. So I won't go into the details here because it's not the purpose of this talk. But if you want more details about why we would like to have proxy execution for Big Little or Big Little-like systems, there's the link to the LWN article of the last OSPM talk that I gave on proxy execution for such systems. But before we build on top of proxy execution for our use cases, we need to build proxy execution, which is why I care. So I said it's aiming to be a better priority inheritance scheme than what we currently have, and what we currently have are RT mutexes. So from an interaction point of view, they look very close to regular mutexes, right? When a task tries to acquire an RT mutex and it's already owned by someone else, we're going to dequeue it. Now, the thing that we're going to do on top is we're going to directly update some scheduler parameters of the task that owns the lock. So say you have a CFS task that owns the RT mutex and an RT task blocks on it. So you're going to dequeue the RT task, and then you're going to update the priority of the CFS task directly and also update its cat class. So you're going to promote it to RT. So that works reasonably well for RT tasks. It's far from being perfect for deadline tasks. So that thing about directly updating a task's scheduler parameter doesn't work for things like contributing runtime. So for deadline, what we want to have is, sure, inherit deadline, but we also want to be inheriting the runtime of the task that boosted us, right? Because deadline is about bandwidth, not just deadlines. And that falls apart. That doesn't work. So what has been suggested by Peter and Yuri is this thing called proxy execution. And the main point is, instead of dequeuing a task when it blocks on a lock, we're actually going to keep it on the run queue. So direct consequence of that is the scheduler is well within its rights to say, oh, this is the highest priority task I need to run out, let's pick it, even though it's blocked on a mutex. So what we can do instead, because it would make much sense to actually run this task, we can keep a reference to it, and then just try and find which other task we should be running to eventually let this high priority task make forward progress, right? Eventually unlock some lock that it can then acquire. So in the previous example with a CFS task and an RT task, it's fairly simple. It can be a bit more convoluted than that. So sometimes I think I mentioned it as dependency chain or blockchain. So it's simply because your highest priority task on the run queue. So the task that the scheduler decides to run might be blocked on a mutex, which is owned by a task, which itself is blocked on the mutex, and you can copy paste this as many times as you want and make a nice staircase. That's your chain. The thing is, you just start from the end, that is which task the scheduler picked, and you unwind it until you reach something that you can actually run and try and make forward progress. So you have those two pieces of information. You have exactly what task is the highest priority one, and then you have what task you can actually run. So what we want to do, and what proxy execution is doing, is we're going to keep a reference to that high priority task to use everything that is scheduler specific for the scheduler decisions and general scheduling of the task that we can actually run. So that thing that we get from the highest priority task is what we call the scheduling context. So it's everything, almost everything that encompasses scheduling decisions. And we still have some restrictions coming from the task that we run, the lock owner, that we call the execution context. So for instance, CPU affinity, it's still within scheduler land, but we don't want to inherit it. Like if your owner is pinned another CPU, it would make no sense to relax its affinity just because it's inheriting from another task. The main thing to remember is about this scheduling context that we are inheriting from this highest priority task. So we are executing as proxy this scheduling context. So the great thing with that is we directly derive our scheduling context from existing schedule logic, right? Because pick next task just picks the highest priority task on the run queue. It's already there. We don't have to reinvent the wheel. One extra complication with that is we want to pick the highest priorities context in the whole chain, like the whole blockchain. So we need to have all of the tasks enqueued on the same run queue, which is feasible, but it's a source of headaches. So that's why I marked it as a negative point. Of course, if I were honest, I would have added a positive for RT-mutex and a negative for proxy exec, which is RT-mutex is already there and working, and proxy exec is still a work in progress. So where we are with proxy exec. So I talked about it last SPM, and you was kind enough to go and fix a few things after I complained. And he got it to a point where if you run mutex lock torture and you cap the number of CPUs to 2, the thing actually survives for over 24 hours. If you leave this CPU restriction, the system dies in quite a dramatic way. So where I intervene in there is I had to spend some time figuring out how proxy execution worked. So when I did that talk at OSPM, I had a brief idea of what it was doing, but to go in there and hack it up, I had to also understand how it was doing it. So that took me some time. And once I was relatively confident in how I understood the thing, I tried to unwind the issues that I was seeing. And one of the big pain points is that task groups or accounting with task groups pretty much breaks. So we end up in a situation where you have a non-zero honor running on your CFS run queue, but the red-black tree is actually empty, and that's a recipe for disaster. So looking into this, I try to see what happens if we don't have to bother with task groups. It so happens that it looks pretty nice. Even if you don't limit the number of CPUs on your system, that survives lock torture for well over 30 hours. So I'll get back on this point. It's only the first stepping stone, right? We can't stop there and say proxy execution watch, it's done and dusted. Lock torture is only the first step, but I think that's on my next slide. I have a few extra fixes on top, nothing major, but I'll go through one of them that I have in the later slide. And so that conceptually, the idea will be for me, okay, I have something that at least survives with as many CPUs as I have on my system, so I'll keep with that without task groups, try and iron out the thing as much as I can. And once I reach something that I consider to be a stable or reasonable base, I'll get back to CFS and try to extinguish the fires. Right. So yeah, I mentioned lock torture as not a final step. And so we are going in there and doing surgery on mutex code. So it's always nice to see that we don't break anything. But we are mostly interested in priority inheritance and executing by proxy a certain scheduler context. So pure mutex log torture doesn't look at that. There is a case in log torture about RT mutexes, which, if I'm right, plays around with RT tasks and changes their priority dynamically. We can directly use that because RT mutex doesn't really stress the proxy exec path. So one thing we could do, and one thing that I like to do eventually, is have a log torture mutex case that does something similar to the RT mutex test case, right? So play with tasks of different priorities. The thing is, as a first inheritance testing step, I thought it could be too much. So I looked into something a bit more static, a bit more simple. And I actually did what I described earlier, right? So you have a CFS task that owns the lock and an RT task that waits on it. You can easily look if this CFS task is placed with an RT proxy. And that wasn't my goal initially, but I ended up testing, can we get RT throttling by proxy? So if this CFS task that owns the lock is a busy loop and it never releases the lock, and that RT task never dies and always waits on it, we pretty much have an RT busy loop, which should eventually lead to RT throttling, right, when we reach this 95% CPU time. And interesting, it turns out that it wasn't the case because we were accounting all of the runtime to the lock owner rather than to the proxy, which goes against what we want to do with proxy execution. So for instance, for deadline, that's one of the missing points we have with RT mutex. We want to be consuming runtime out of the proxy, out of the donor, the block task, to eventually hit runtime enforcement if the owner task is misbehaving. Might not be the right term because it wasn't designed as a deadline task, but not behaving in the way the proxy task was described for deadline policies. So if you look at the code, it's a very simple fix. That's what I have in there. You just flip from current to proxy. But figure out that this was broken and this fix was recurred wasn't obvious to me at first, right? I had to dig in there and have something that spurred the investigation. So there's a fix for that for DL and for RT. CFS wasn't affected because of the way we update runtime. It was already doing the right thing of updating the proxy, or accounting to the proxy and not accounting to the owner. This, however, sparked, let's say, potential issue for me, or at least something that I see as what could be a problem, and that is the user space side of things. So it's the same scenario I was describing. You have this CFS task that's a busy loop that holds the lock and never relinquishes it, and you have the RT task blocked on it. It's an extreme case. You really shouldn't be having things like that out in the wild. But if that happens, you have proxy execution, and you try to look from the user space side of things, what's going on, you're actually going to see the task that is blocked, the task that actually didn't run on a CPU, consuming all of your CPU time. Because effectively, we are using its scheduling context all of the time, and we're always accruing runtime to it by proxy, but it's not actually running. The thing is, user space currently cannot make the difference. So if you look at this, you have 95% of the time that is accounted to the task that's blocked, and the remaining 5% for the owner. And that's just because of RT throttling, right? We have 95% of the time where the owner is boosted as RT, then the RT run queue is throttled, and the owner is still running, but this time as CFS. If you look at the same scenario with RT mutexes, where we don't use a proxy, we directly update the owner, you have something that, from a user's perspective, is much clearer. So the question that I raise here is, how worried should we be about this, knowing that this is let's say, the worst case you can have, but it's going to influence any sort of performance analysis you might be doing when all of that time is accounted to the proxy. And worst case, do we actually need to consider having two different accountings, one where we account runtime to the proxy for scheduler distributions, and one where we accounting to the owner for, say, user space reporting? I don't know if people have opinions on that. That would be the first quickly point for me.
Yeah, I guess I would try to do that. I currently don't see another solution. I guess I'll have to think about it. But yeah, I mean, one thing. Again?
Do you mean the dual accounting?
Yes. Yeah. or at least report in somewhere to user space that the owner is actually running instead of the developer.
Yeah, so there either needs to be a way to directly report the runtime to the task that's actually running, or some way for user space tools to unwind. I don't know how much we can delegate that to user space and how much needs to be done in kernel space.
Is there a way to figure out or maybe export a way that like the PE owner was running as a proxy?
Yeah, so we could, it depends how accurate we want this bucket to be. We could have a bucket that says that's the time we run, not as proxy or being proxied by someone. Then there's the thing I'm wondering is, yeah, how accurate we want to be on this. Do we want to differentiate different proxies, or is one bucket sufficient?
Because I was thinking, if you have it so that you, like the first one, I guess I'm assuming that the PE blocker is really blocked most of that time. It's just that it's, the PE owner is running.
That it's never relinquished. It's never actually running.
Right. So it's never actually running, but it says it's running. It has 95% of the CPU, and that will probably confuse the hell out of users when they go and say, it says it's running, but it's not getting anywhere. So that's no. You can't have that top one.
So it's in the case that we have some other wrongly placed pointer, like in the previous slides, where you actually change the proxy and core. I was thinking that maybe there is something like that. I mean, we are using the wrong in the load average reporting, or where user space gets these numbers, maybe.
So as far as I'm aware, that's directly from the accrued runtime of the task, and so like I think for top we fish this out of proc PID stat or something.
Right.
And as far as I'm aware, that's directly derived from. I don't think I have the actual code in there, but we figure out the delta exec and we account that in the summon exec, and I think that's what's being used down the line.
Yeah. So yeah, I guess one thing that we might try to do is, as you basically were thinking as well, to basically create a shadow thing we can use to give this kind of stats to user space.
Right. Yeah. Yeah. That's. I guess I'll see how bad it behaves, but I think, as Steve said, we can't leave, and that was my worry as well. I don't think it's acceptable to leave things as they are.
Yeah. Yep.
Right. Any further comments on that? Not on. Move on.
Well, I'll start. Just real quick, just so basically, yeah, I mean, I see what you're saying, but for the accounting wise, you may have to do something different for decision making than what is actually reported. But we definitely have to have that separated out somehow.
So for decision making, what we are seeing is what we want actually. We want to be accounting always to the proxy. It's just that from a user space side of things, that's not what we want.
Correct. Yeah, that'd be definitely a no. I mean, the user space side should see actually how much it's running, but it would be interesting information to say that it's mostly blocked and it's giving its proxy. So maybe we needed some sort of API to user space to export this information. That'd be very useful.
Right. Yeah. So right now, the only thing you see is if you look at the state, you'll see that it's running, but it's not the most informative thing, let's say. All right. So the other thing that I have, somewhat unrelated, but is also like, it's a building block for proxy execution, which is, yeah. So as I mentioned, we have this blockchain or with this dependency chain that we need to be able to unwind. And one change that we have in the patch set for that is we make every mutex unlock a handoff. So to put it simply, what is mutex handoff? So when you release a lock, what you can do, what happens is you look at your waiting list, who's waiting on this mutex. Okay, let's take the top waiter and wake him up. but you don't reserve the mutex for it. You clear the owner field. And so what can happen is someone else, some other task, can come in and grab the lock before the top waiter gets awoken, however that is. So the thing is then when that waiter, or when that waiter, wakes up, it can realize that, okay, someone has stole the lock, so I can set a special flag, which is this handoff, which is at the next unlock, keep it for me because I don't want this to be happening all day. The thing is, we need to be able to unwind this dependency chain, so we need to reliably be able to use the mutex owner of a mutex. So proxy execution sets every unlock to be a handoff. One thing I'm slightly worried about, and the answer might just be keep it and then implement what's missing and see what performance numbers you are. But conceptually, I'm slightly worried that it's going to affect the mutex operation performances too badly. So it might just be that I should ignore that for now and carry on and then do some performance analysis. But I figured it would be worth raising and see if that's something we should look into before going further.
So what's the I'm a little confused on what the change that you're asking about here. I mean, right now we have the well, there's a fast path and slow path for the unlock, which is if you have a waiter, it's going to fall right into the slow path, and if there's no waiter, it just flips over. It's an atomic operation. It goes right off. You're not going to modify that, I'm assuming. No. Okay, so this is only in a slow path.
Yeah. The thing, what this is going to change, it's going to mean that as long as you have waiters in waiting list, no optimistic spinner is going to ever succeed. That's the change that's introduced by the proxy execution patch set.
So as long as you have wait, there's no. Let's just say wait. What's it called? The spinning. I can't think of the term that's used, but because right now, yeah, if you get it, if the owner's awake, you'll spin and try to grab it. You're just saying that there's another waiter and you're going to fall out.
Optimistic spinning, I think. Yeah.
Really? So we don't. So if there's waiters, we could still do that.
As far as I'm aware, maybe I'm wrong, and in that case, that's problem solved.
Well, actually, I think everyone would be spinning then. You have multiple people spinning, and they'll be all fighting it. But you're right. I have to take a look at that. I don't think we're still allowed to spin if there was. Well, I guess you could. Well, you still add yourself to. If you're a spinner, you still add yourself to the top waiter, I thought.
Okay, in that case.
And you only spin. You should only spin if you're a top waiter. If you're not the top waiter, you should not spin. I have to go look at the implementation.
Well, I think it's like a different waiting list, which may be where I got confused. I think the optimistic spinner, they have a different serialization.
Yeah, I haven't looked at the code in a few years, so I have to go back and look at it.
Yeah, I just started looking into it. So.
But yeah, I would definitely agree that if you have, you should not allow a lower priority process to steal mutex if it's a higher priority process is spinning on it.
Yeah, so that with proxy execution, that's prevented because then how does that work? Yeah, we select the next owner as the directly lower priority task. So we're actually using the scheduler priority ordering to do the unlock or to pass the lock, which is probably good. But then we also have in the one thing where optimistic spinning might actually be hit. But yeah, that's something we'll have to see further down the line, I think.
Yeah, just check it. And yeah, that's something we'll just keep an eye on. But I don't think it should bother you.
Okay, cool. Thanks. How much time do I have left? 7 minutes or so?
7 minutes, yes.
Yeah, okay.
7 minutes.
Actually, I can go to one of the only backup slide that I have. And this is only really, let's say, speculation. So one thing that is marked as a to-do in the series is migrating this dependency chain. So as I said, we need the whole chain on a single run queue to do the right decision of which context to inherit. The problem is right now, this happens in a staggered fashion. So if your chain is spread over several CPUs, what you're going to do is as soon as you see an owner or a task that you need to migrate that's involved in that chain that is on a different CPU than the current one, you're going to halt off your operations and then migrate everything to that CPU, or migrate the parts of the chain that you've seen to that CPU. And then once you get to scheduling on that CPU, you will carry on until you maybe again hit another task that is still on a different CPU. So the whole migration of the dependency chain happens in a staggered fashion. So the speculation part for me is, I'm wondering if this might not be where the accounting issues happen for CFS, and if we can think of a better scheme there. One thing that I'm worried is if we try and do the same in a single go, then we would have to grab all of the RenQ logs in one go. Or maybe not the right expression, but in a single proxy execution call, we'll have to go through all those run queues to dequeue the tasks that we want to move around and migrate them to the final owner. So I don't know if we can think of a better scheme than what we have right now. I clearly haven't thought of anything better right now. So if there are any better ideas, I'm taking. Otherwise, that's going to be the same as the mutexes. I'll keep carrying on. I'll carry on with what I have right now and see if that, when I get back to CFS, if that's actually the source of the problem or if that came from somewhere else, and if that's a problem for performance and needs to be fixed.
Yeah, I think also Peter is already calling out the problem, or at least the potential improvement in the series. I think there is a comment saying, I mean, we are doing this right now, but of course can be improved. Not sure how as well, though. I guess, I mean, we are currently doing that because, as you said, there is a chain of tasks, and we need to find the highest priority one from which to inherit. I'm not sure if it's possible to only, I don't know, maybe only migrate the highest priority one, but then how do you ensure you are picking the right one? I guess if not everybody is on the same run queue at the same time, right? Yeah.
Yeah, that's the problem. Right?
So wait, I'm a little confused. Wait, what exactly is the problem again?
So we have this dependency chain, right? Several tasks blocked potentially on several mutexes, and at the end of your chain, you have one task that you can actually run that is not blocked on a mutex. So the problem is we need all of this chain to be enqueued on a single run queue because we want pick next task to pick the highest priority task in whatever dependency chain you might have, or in that dependency chain, right?
So wait, you want everything on the same run queue?
You need to, yes. Because the point is we are piggybacking on the current schedule decision, which is, okay, on this run queue, I'm going to pick the highest priority task. And then if that task is blocked, we use that to do proxy execution. So if you have your dependency chain strewn over several run queues, that's not going to work because maybe you're going to pick a high priority task, but it's not going to be high priority enough if you look at the whole dependency chain. So for ATMutex, we do that because we dequeue everything and we have our own data structure. But here we're relying on the scheduler data structure of the run queue, and we need everything in a single place to do the right decision.
Okay.
It's the fun part. One of the fun
So
parts.
I guess the difference is that still we need the RB3 where to store everything, as you said. RTMutex has their own internal RB3, and we are basically piggybacking on the run queues RB3s in this case. So we have to get those tasks enqueued in the same RB3 to pick the highest priority one.
But you can't move them over, though. I mean, you can't, if a task is on another CPU, you can't just queue it on, unless you make it like a virtual run queue.
Well, so the thing is, if they are in the dependency chain and they're not runnable, they're blocked. So we are pretty much free to move them on whatever run queue we want. So there's some trickiness. When they actually become runnable, we need to move them back.
Oh, I see.
But for scheduling decision and proxy execution, we're actually free to shuffle them around.
Maybe we should look at some sort of like virtual type of run queue or logical run queue type of thing. I don't know. Added another hierarchy somehow. Just throwing out a brainstorm idea. I don't know.
Yeah, that's more than welcome. Thank you.
Yeah, instead of like pinning to like say a run queue actually represents a CPU, maybe I have all the run queues kind of like virtually attached to CPUs, so you can move things around without actually worry about scheduling on the same side. And time's up.
Yeah. Anyway, yeah. Thank you. Thanks everyone for pitching in, and that's it for me for today.
Thank you, Valentine. And now it's time for our last talk of the day.
Let's see if I can get over to my slides.
Well, say, Rick, you work for ARM?
Well, that's my fault. I'm a little slow right now. Is this the one? Did I get the right one?
Yep, that's it.
Okay, perfect.
First two slides are the same as last year because it's still the same problem that I'm working on. And after that, I'm going on to some new stuff. I tried to keep the number of slides small because as a suspect there will be a bunch of stuff to talk about.
So you should have presenter mode right now.
Yep. The problem that we have with the C group CPU controller right now is just overhead. And last year I presented an idea on how to fix it that had some flaws in it. Paul Turner, who unfortunately does not seem to be here today, he found a few corner cases that seemed like they might be insurmountable issues. And a month or two ago, I came up with ideas to hopefully fix those. But anyway, let's go to the start, C group CPU controller, where we have an issue with overhead. The task, something like Bill's audio, does a lot of wake-ups and sleeps every second. Might be hundreds a second. And every time a task wakes up, the task gets enqueued on the run queue of its own C group, which then gets enqueued of the C group above it, above that, and then finally onto the root. So every time a task wakes up and goes back to sleep, we build up the entire hierarchy. Every time a task goes to sleep, we tear it down, we update the V runtime everywhere. And decisions like preemption and time slicing are evaluated at every level, which is a lot of overhead that is unnecessary on most systems, because most of the time your CPU will have 0 or 1 runnable tasks on it. And we're going through a ton of overhead for no good reason. We have seen as much as 3% overhead from the CPU controller. And the overhead comes mostly from cache misses on all the data structures in the hierarchy that we walk on every wake up and every sleep and every timer tick for the current task. And the basic idea in the design is to reduce this overhead by limiting how often we walk the hierarchy and by using only the top run queue for all the tasks that are running.
Rick, so do you confirm that your problem is mainly for use case where you have only one or no task enqueued on the full hierarchy and you want to, or you have other use case?
It's not necessarily that about a specific use case like that, but about the fact that most systems are not horribly overloaded and have some idle time. and have a number of runnable tasks that is usually near 0 or near 1 on each CPU.
Okay.
And there are some corner cases that the hierarchical system deals very well with. But if we can get rid of the hierarchy for wake-ups and sleeps and making scheduling decisions, for most of them, we can cut out a lot of the overhead. And we just have to figure out a way to directly put the task on the root run queue every time. And it all comes down to the idea that every task on a run queue that is runnable gets the same amount of runtime. This, with the C groups, it will be true on every level individually. Where on each level, if you have a task or a group, this one will get all of runtime that's accumulated here. And if there's a split here, then if runtime will be split between whatever is running on this side and the thing running on this side. But the way hierarchical, if we do the hierarchy walks, there's a thing called task hload in scatfair.c, which basically calculates the hierarchical priority for each task. So we already know that, let's see if I have that here. Yeah, something like this. We know that each task has a certain priority that is derived from the priority of the C group it is in and from the task priority itself. And in this case, we have 3 tasks running where the C groups are both equal weight. And we know that this task should have roughly half, or should say this task should get exactly half of the runtime on the CPU, because half of the weight, it's the only thing in a C group, and this C group has half the weight of the total weight in this run queue. And on the other side, we again have a C group with a weight of 1024. But this run queue has a slightly different weight than its own SCAD entity. There is this really low priority task, which should get a little bit of runtime. And we have this really high priority task over here that gets most of the runtime in the C group. This works well with the current hierarchical setup. If task 2 were to go to sleep, then task 3 would automatically and instantly get all of the priority of this whole group. At that point, the CPU would be fairly divided between task 1 and task 3. The thing that I presented last year, where we use the runtime and we scale it with the hierarchical task weight, where basically the lower the hierarchical task weight is, the larger the multiplier ends up being. So if you run for a microsecond, or say a millisecond, and we have a task at a super, super low priority, then the runtime would be advanced by an enormous amount, which Paul Turner pointed out is a problem here. If task 2 wakes up and goes to sleep and wakes up and goes to sleep, every time task 2 is sleeping, task 3 should get the full priority of the C group immediately. And both task 1 and task 3 at that point should get 50% of the CPU. So we need a way to converge the priorities to the actual hierarchical priorities faster than the thing that I presented last year, where if task 2 were to go away, the hierarchical priority of task 3 would be the full 1024 of task 3's C group.
Hey, Rick.
Go ahead.
Hey, I had a question on the previous slide. So with your work of like flattening the run queues, in this example, what would be like, say task 2 went to sleep, what would task 3's priority look like?
There's two things here. There's the priority, and there's the view runtime.
Yes.
The priority, the hierarchical priority, since task 3 would be the only thing running in run group B, the hierarchical priority of task 3 would be the full weight of its C group.
That's what it should be, right?
Yes, exactly.
And you're saying that if you flatten the hierarchy, you no longer have that.
If you flatten the hierarchy, you do have it, but an issue is the code that I had last year. If task 3 were to run for some short period of time, we might move its runtime all the way from over here way into the future. And then task 1 could have a whole bunch of time slices before its view runtime would catch up with where we placed task 3 on the virtual timeline.
I see. Okay.
The problem is in the current, I didn't actually understand the problem in the first place. That's why I asked you again on the list. But I think you explained it like later that because in the current setup, it doesn't matter the weight of the task, right? Because if the task is the alone shed entity in the run queue, then check preempt tick only considers those shed entities which are not alone on the run queue, which would be A and B, which are in the root run queue together, and they time share. And that's why you have this nice thing that task 3 immediately gets half of the time. Whereas
exactly.
In your approach, which you base on task, an SE weight hierarchical, the task itself, it's on the root run queue, and actually it has its own low weight inside. So it will be treated like a shed idle task, what you just said, that the runtime is way in the future. Yeah.
That's old stuff though, right? Maybe he's trying to explain the new stuff and we should hear out what he has to say.
Well, I wanted to explain the old problem. I probably should have made another slide on that too, since it is somewhat subtle. But the solution that I came up with, where instead of moving the view runtime all the way into the future with the entire time that a task has been running, we could cap the amount of view runtime that we account at once to something like scat latency. And if they have a task like task 3 in a previous example, if it's running at the same time as task 2, it might have gotten a longer time slice than we can account from the wall clock time delta exec into view runtime at once. At that point, we can consider this task to be overloaded, and we can move it to a separate run queue, or a separate run queue heap on the same CPU, which would also be sorted by view runtime. And then in pick next entity, what we can do there is we can look at the leftmost entity in the overloaded heap, and we can give that as much view runtime as it would need to get up to date to the current view runtime. But never more than needed to account all of its delta exec. If the task still has delta exec remaining, so it has more wall clock time that is still not accounted, we can simply put it back on the overloaded heap, and we can run a task from the main run queue. And we can move one task at a time back from the overflow queue to the main run queue. This way, the low priority tasks should not starve tasks that are already on the run queue. And the longer a task sits on the overflow heap, the more view runtime it could get at once, which means that the tasks there should not get starved, unless I overlooked something fundamental here. And we should still preserve the O1 properties of the scheduler. It's unfortunate that Paul and Peter are both not here because I think they would have had some comments on this, but
Might want to go ping Peter and probably talk to him maybe in a hack room. He was in the, I think he moved over to the ARC micro conference.
okay.
And if anything, we'll try to get these out. Maybe you just have him go watch this, watch your topic, and then talk about it.
I also just ping Peter to see if he can join.
So Rick, your solution there seems to complexify all the things. At the end, are you sure that you will get benefit compared to the normal hierarchy? I mean, that's why I was asking you if there is some use case. I mean, I agree with you that if there is only one running task on the run queue, you can probably optimize that to directly schedule, and because you don't have to take care of the mean runtime and so on.
If the number of tasks on the run queue is small, then they will all get a time slice according to their priority within SCAD latency. So if you have less than half a dozen or so tasks on a CPU, then they should all stay on the main run queue.
In fact, the rule would be if you have one task per first level of C group. In this case, it's quite easy because you can directly map everything. But if you start to have more tasks in the first level, then you need to go through the hierarchy to split and update the mean runtime.
Even at that point, I think if we have a smaller number of tasks, they should still be on the main run queue. The overflow run queue would only happen if we have enormous priority disparities between tasks and a larger number of tasks on the run queue. And at that point, only the tasks with below average priority could end up getting moved to the overflow run queue.
But in your example, you had one normal task and one task which essentially has a lot of B runtime already. And in this moment, you have only two tasks, but you're saying you still want to move it to the heap?
The reason for moving it to the heap is we moved it to the heap while task 2 was still running. And task 3 had really low priority. Because at that point, we could not account all its runtime in SV runtime in one go. However, once task 2 goes to sleep, then we check task 3 on the overflow run queue, and we will see that its new hierarchical priority is the full priority of group B. At that point, we can account the remaining runtime that task 3 had at its new hierarchical priority.
Okay, so it will actually forget his low weight when it goes back to the main run queue.
Exactly, it will have the rest of its runtime accounted at its new higher weight before it goes back to the main run queue, which means that the V runtime is where we need it to be for task 1 and 3 to get an equal amount of CPU time.
What about, Rick, things like, say you had a task 4 in D, and that had like weight 1 as well, and task 2 went to sleep. Would this scheme divide the time that B gets by 2 between task 3 and 4?
Yep, it would. They would both end up with a hierarchical weight of 512. At which point, task A would get a time slice that is half of SCAD latency, and task 1, and task 3 and task 4 would each get a time slice that is a quarter of SCAD latency, and all of them would be able to get their runtime accounted while on the main run queue without ever having to move onto the overflow run queue.
Okay.
A question I had when I saw this, and I actually understood it the second time, how is this related to CFS bandwidth control, which you also had ideas to park those tasks then on those shared entities of the task group?
Oh, that brings us to slide 5, which is another objection, a corner case that Paul found, which is thundering herd wake-ups. If you have one task running in C group A, and you have 100 tasks waking up in C group B, how do we keep the task in C group A from getting starved off the CPU for an acceptably long latency? The only solution to that is admission control, which in a hierarchical system is accomplished automatically because we time slice between C group A and C group B, and inside C group B, we pick whatever task we want to run each time C group B is chosen at the higher level.
Also, Rick, if I remember correctly, you are not updating the hierarchical weight of the task each and every time, but you have some rate limit to that, a tick at most.
We update it at most once per tick, but
which means that if there is some wake up and sleep during this tick, the hierarchical weight of task 3 will not change, so it can be maintained at a higher value than it should be. Isn't it?
It's true, but only for the period of one tick, which is much less than SCAD latency.
Yeah, but can you provide more running time? Isn't a way to get more running time that you should? Because it means that at some point you will have all the 3 tasks with almost the same weight, whereas normally it should not be possible. Either task 1 and task 2 are almost the same, and the other one is small.
If task 3 starts running with too much weight, then when it gets descheduled and we try to account the time into vruntime, we will probably notice its new weight. And then we might have, oh, we ran way too much. Let's put this guy on the overflow run queue for a little bit.
Yeah, my point is that the weight will not be aligned with what it should be, because you will always be, you always be behind the real weight. Let's say that you see what I mean?
Yeah,
that's
it may
not possible right now.
Immediately converge, but in the current scheme, it also does not immediately converge, because the value of each run queue's SCAD entity is calculated as the weight of the C group divided by the weight of all the tasks inside the C group on all the CPUs. And if we have a C group like this with 6 tasks spread across 5 different CPUs, then if task number 7 wakes up, this C group entity here is going to have the wrong weight for a little bit of time, even in the current system. So we are already working with slightly stale values sometimes, because it is way too expensive to always iterate over all the CPUs and recalculate this value.
Yeah, but this is happening between CPU. On the same CPU, this is not happening. You are adding one more variance in the fairness in the running time. What you're saying happened because when you have SMP or multiple CPU and you have to share the weight across the CPU. But if you just use on one run queue at a time, this is not happening right now.
True. Though,
that's my point.
Yeah.
Which mean that we'll lose some accuracy.
Is that true when a task goes to sleep on one CPU and wakes up on another?
Yeah.
Okay.
You have that was a discussion. Yeah, you can't provision some things like that. But that might. Yeah, I don't know. I probably need to dig more deeply in your proposal. But what I'm afraid is that at the end, if you have more than one task per first level of C group, you will end up doing to be as complex as going through the full hierarchy. That's why I was asking you if you have some, if you want to be like that for any kind of use case, or if you have some use case like maybe one task per C group is the one you want to optimize, which is quite straightforward because you don't have, I mean, you don't have really to update the hierarchical weight of each task, and
Well,
you don't have to take care of that.
The common cases that we see are really we have one or two tasks from a workload on a CPU, and they might wake up a kernel thread.
Okay, which means that they are not belonging to the same C group.
Yeah, and the tasks in the C groups and the kernel threads might have over 1,000 wake-ups and sleeps a second.
Yeah.
Well over.
Maybe, yeah, I think this one should be quite easy because at the root run queue, the first level of a selecting the SCADA entity, I mean, you don't have to split over, so that could be quite easy to optimize that. Your problem is that when you start to have to then split the weights and split the way you are counting the VRun time.
Yeah, and well, it's got a 5-minute warning, so I'd like to go through the last slide as well. The objection that I got to the overflow run queue is that it adds complexity, but I believe it solves all three problems at once. It solves the too long time for convergence when a task's VRun time is increased by way too much at once. It can solve the Sundering herd by, at wake-up time, we can check, hey, is this task priority so low that it could not possibly run for even a min granularity and still have all its VRun time accounted? If so, then we can probably wake it up on the overloaded run queue instead. And we can also use this overloaded run queue heap for doing wake-ups from CFS bandwidth, where we can place either tasks or simply groups that were woken up on this overflow heap and apply essentially the same rules there. So I think this one thing of complexity would solve all of these three different issues. Is that something that makes sense to you guys?
I have to say, like, given the fact that the last patch set is like a year old, and in the meantime there were like other changes, it's very hard to reason about the model. I mean, it's
yeah,
very
agreed. I do need to implement this at some point and
I think if we
come
would
up
have
with the benchmark numbers.
Yeah, if we would have a patch set to play with, I think it would be easier to evaluate.
Yeah, to answer Joel's question as well, the overhead mostly came from cache line misses. When enabling the hierarchy, I see an equal amount of CPU use increase in the kernel and in user space for a fixed amount of work. So we have the kernel getting cache line misses. That's also where the time is accounted when you look with perf. It's all things like move instructions and loads and store, stuff like that. Just memory accesses from having the multiple levels of C group. That's where the overhead is. And the overhead incurred in the kernel by accessing extra memory is then duplicated in the user space side by the kernel evicting user space stuff from the CPU caches. So when we go back to user space, we end up having the same number of extra cache misses in user space as well. And it's not as much a code optimization where we can make things faster, because we just have to look at the data that the kernel currently looks at in the hierarchical model.
Since we only have one question, there is only 1 minute. There's one question for me. Maybe it's easy to answer for you. The moment this one task disappears, which makes task 2 the only one in this group, you must at this moment, you must actually recalculate task SE hierarchical weight for this task 2 to know that all of a sudden now it doesn't have to suffer its small own weight anymore. How is this achieved?
We recalculate the hierarchical weight once per tick, basically.
Okay.
And we would also look at that from pick next entity. If we see, well, hey, this task has an old hierarchical weight, we should recalculate it before accounting delta exec into the runtime.
Okay, thank you.
Well, thank you, everybody.
Rick,
And
one
if you
last
want
thing.
to chat more, I'll be in the chat.
And where's your patches?
I don't have any current ones because I spent the last few months changing diapers.
Ah. From the scheduling folks?
No, that's after they see the patches.
Thank you very much, Rick.
Thank you,
Now you have
guys.
to tell us which is a dirtier job, Rick, changing diapers or changing the scheduler.
Oh, man, that's a tough question.
That's what I thought.
Thanks, everyone. Make sure you guys, make sure you record the public chat or download Davo. I think, did you download it and the shared notes?
I'm going to do that. Yes, I'm going to do that. And before we get done, I want to actually thank everybody else who's been involved in organizing this. Thank you to the LPC organizers, and thank you to everybody else who has helped organize this, and thank you to all the speakers who are part of this, and thank you to everybody else who helped in the discussions today. This micro conference could not have been a micro conference if you guys would not have contributed. Thank you.
See you, Davo. Bye-bye.
Daval, for the BOF tomorrow, how do you advertise the...
So we have 8 a.m. onwards. I'm going to go talk to the folks on Rocket Chat and see if we can get a room assigned to us and put it in the official schedule. I think they have like 3 different back-to-back sessions that they want to have. So we'll probably just occupy the room